Can everyone hear me loud and clear? Great. I think we need to get started. We have a really, really dense program, so could everyone get settled down? All right, so good morning, everyone. My name is Ali Hassan Ali. I'm a part of the faculty here in the Condensed Matter and Statistical Physics group. It's a real pleasure to welcome you all here today to this activity. Wonderful to see a lot of old faces and then a lot of new ones as well. And so I want to actually do two things in the first part of the presentation before we move into the actual scientific program. The first thing I want to tell you is a little bit about ICTP, because I know there are a lot of new people here who may not know a little bit about the historical context, and then a bit about the program. So we are at the Abdus Salam International Center for Theoretical Physics. This is Abdus Salam. So Abdus Salam was a high-energy physicist who got the Nobel Prize in Physics in 1979 for the electroweak unification theory. Abdus Salam was interested in other types of unification. And in particular, Abdus Salam was a native from Pakistan. And so he had been exposed to the challenges of doing science in the global south, so to speak. And so one of his visions and his missions was that, essentially theory, doing pen and paper work, working at a blackboard, is cheap. So, this is something that one could try to build capacity on in parts of the world that have challenge in these things. And so over the last, during his tenure as the founding father, he created a lot of programs to combat scientific isolation. And so this is an example of an event that took place which brought together people from different parts of the world looking at, for example, nuclear fusion at the time. Last year, we celebrated our 60th anniversary. And one of the questions you may ask is, well, what is the relevance of ICTP now? And so over the last 20 years, and this is this community is a great example of this, the science of high-performance computing has really revolutionized and changed a lot of how we do our science. And we're going to hear a lot about this over the next week. But the culture of doing atomistic simulations, computing, but also using computing to learn new physics, new chemistry, new biology, has really transformed the way we do things. I don't want to sound like I'm getting into hype, but even if you renormalize by hype, there's no question that AI, machine learning, is changing the way we're doing things, the way we're doing science. And I just picked up a couple of these different articles where AI is changing the way we do biology, diagnostics. And the last one is particularly interesting also for us at ICTP, which is AI being used to translate books into languages that allow people, for example, scientists, to be able to read in their own native languages. So I think the opportunities are really open. So what's the typical type of challenge that we at ICTP deal with? So this is Daniel Shadrach. He's kind of our poster child. He was a former student of mine from Tanzania. And his type of question is, I would like to use computers to design drugs. And so how does he do that, right? I stole this article from the New York Times, which shows the global AI divide. So these are the bright colors are where all the AI data centers are in the globe. And as you see, most of them are present in the global north, okay? So last year, ICTP launched something called the International Consortium for Scientific Computing, which is led by Sandro Scandalo up here in the front. And I won't get into the details here, but the key thing that we're trying to do here is to democratize access to high-performance computing and AI. And for the Africans in the audience, I just wanted to advertise this. The first initiative in this direction is a partnership with CCAM. There's a call for proposals to get access to high-performance computing in the broad area of atomistic simulations in the topics that are covered today. Okay, so that's a little bit about the history of the Institute and where we are at the moment. I want to say a little bit about the program. So the program is Conference on Frontiers of Atomistic Simulations, Physics to Chemistry and Biology. Let me start by thanking all the sponsors, without whom this event would not be possible. This event has been led by a very dynamic team of co-organizers. I will not list them here, but I want to particularly thank Ariel. Where's Ariel, by the way? Is Ariel here? No. Ah. Okay. Ariel, Francesco, and Paolo, who were really instrumental in getting this program together. Another person that you've heard a lot from over the last months is the Secretary, Victoria. Victoria is probably, where are you, Victoria? Are you here? Ah, there you are. Can everyone please give Victoria a round of applause? Without her, this event would really not be possible. So as I was trying to put this program together, I needed quite a bit of therapy, okay? And so, you know, I turned to my personal therapist, like many of you maybe, ChatGPT. I uploaded the program and I said, well, any thoughts on this list of speakers for the conference I'm trying to organize this year? Okay, so through some other stuff about the thematic topics of the program, eventually it ended up with this overall impression saying, this is the kind of lineup that signals a landmark event. Not just another conference, but one that traces the past, the present, and the future of molecular simulation. Okay, pretty good. So after a couple of other iterations with it, we end up with the following, and we tried to keep it a surprise, but unfortunately we failed. And so the conclusion here is that the single one person who stands out as the unifying lineage is Michele Parrinello. He connects Parrinello molecular dynamics, metadynamics, and the enhanced sampling machine learning generations represented heavily in your program. Okay, so surprise. So that's a bit about the program. So Michele, of course, does not need much of an introduction to many of those who are part of the ICTP community and many of you participants, but I wanted to share a little bit for some of you who might not know him and who you will get to know over the course of the week. Michele has had a very long relationship with ICTP. This is a picture of these two young lads in an activity in 2001 on the frontiers of condensed matter computational physics. Michele and Roberto, in fact, won the Dirac Prize for their contributions to, you know, the Parrinello method in 2009. And here at ICTP, we like to think that a lot of the magic happened within the walls of ICTP. I don't know if Michele agrees with this. I know everything started in Messina for you, but I think a lot of the interesting stuff started here. And so it's a really wonderful to be hosting this here, this event. Michele has also played a role for about 10 years in our scientific council, advising the director on the strategy of the institute. And so that's kind of Michele at the institutional level. At a more personal level, I wanted to share basically three things. And so my entire relationship with Michele boils down to 3 emails. Very simple, okay? So this is me, a young lad, really a young lad, in the United States. Well, you know, I had a Discman at the time. There were no Discmans, okay. Anyway, and I was reading this paper by Giovanni Bussi and Davide Donadio, who are sitting in the audience here. And I was like, this is a really cool paper, and this would be a really interesting place to go to and to work, and a person to work with. So I wrote to my supervisor, Sherwin Singer, and I said, Sherwin, what do you think about doing a postdoc with Michele Parrinello? And basically, Sherwin responds in about an hour, and he says, hey, Ali, you can try, but don't be disappointed if he doesn't respond to your email. I said, fine, thanks for, setting my expectations. And so I write Michele an email, I think it was a Friday night, and basically, in a day, Michele writes to me, he says, I find Skype a bit awkward. How about I fly you to Lugano for a chat? Instead, looking forward to it. Okay, so, great. So that's email 1, which had a huge impact in my own scientific career. The second email was basically we used to hang out a lot at that top floor there, the 5th floor where his office used to be, laughing, and I'm sure those of you who know Michele very well. And I was thinking about my career, and I made one comment to him. I said, well, I'd like to be able to contribute to science in Africa. Okay, this was something that I felt very strongly about. So I think, again, it was on the weekend. He goes away for the weekend, and he sends me an email on Sunday and says, "Hi, Ali, I'm thinking about your future. I think you should try to get a job at the ICTP. Let me call my friend Ariel." Okay? And then, well, the rest was history. The last email, I think, really nicely summarizes how Michele combines fun and science together. And so I was at a conference in Telluride, and Michele drops me an email saying, "Hi, Ali, just checking in. How are my old friends, Eigen and Zundel, doing these days? Still causing trouble, I suppose." So I don't know how many of you are familiar with this Eigen and Zundel thing. It's been a very fun, kind of lively area of research. I'm not sure I answered your email at the time correctly, but now I can tell you, Eigen and Zundel are dead. But we give you now Zundeig, and I have a gift for you, actually, Michele. It's a little model of Zundeig, and in order to understand it, you're going to have to read our paper. Okay, so now the last thing before I hand over to I have the last thing to tell you, which is, no. Okay. Okay, this is supposed to play. Give me a second. Okay, let's try it here. I hope you can hear it. No.
تولدت مبارك. Birthday. Buon compleanno. Buon Conan. Feliz cumpleaños. Alles zum Geburtstag. تولدت مبارك.
No, it's so this is not how we were supposed to go, okay? But, so let's do the following. I'm going to do this, and wait.
Alles Gute zum Geburtstag. تولدت مبارك. Shubhodon Modin. Schreitenrodenden. Joyeux anniversaire. Nitrogen. EQOJOEB. Heria Sikwe Kuzaliwa. Chronia Pola. Yomuledet Sameach. Setko Nailepsiek Narodeninam. Ge feliciteerd. Janmedin Gishubkamnai. Tilhamin Kimedama Elif. Nzoni Fini. Awofo Danu. Wazalwa Kurungi. Feliz anniversario. Sengil Chukaheo.
This is Happy Birthday, Michele, from all the 25 languages of the people, participants of this activity. I want to end by saying I enjoy this event. I hope you will enjoy the science. I want to welcome you all again on behalf of the ICTP community, and I think we can get started with the first show. Alessandro Laio is the chair. Thank you very much.
Well, I'm almost crying, I have to say, because seeing so many faces that I know here and having the honor to chair the first session of this meeting for me is a really, really an enormous pleasure. I'm simply happy. As ChatGPT has correctly said, here we have the community which has been building molecular modeling across the years, and I'm actually proud to be part of it, and I'm proud to chair the first session of this meeting, which I'm sure is going to be great. So the first speaker is Pablo Piaggi, who will tell us about understanding crystallization with ab initio machine learning simulations. Please.
Okay, I don't need the mic, thanks. Yes, great, thank you. Okay, good morning everyone. It's an honor to be here celebrating Michele's birthday and achievements. So this is the title of my talk, but I will try to focus on some things I learned from Michele over the years about simulations and also much more, I think. Okay, one thing I learned was to tackle challenging but also useful problems of practical relevance, and the problem I chose in this case is the crystallization. I will give some examples to motivate the research on this topic. The first is climate change mitigation via mineral carbonation. So the idea of taking CO2 from the atmosphere and locking it into carbonate rocks. The second example that I would like to put forward is the manufacturing of pharmaceutical materials. So most drugs are at some point crystallized in order to purify them and to create a powder with suitable properties for further processing. And the focus of the research will be on, I think, what Michele would at some point call rare but important or crucial, I would say beautiful fluctuations that dominate some processes such as conformational changes and first-order phase transitions. In the case of crystal nucleation, a very successful organizing framework for the theory is classical, for the phenomenon is classical nucleation theory. So here we consider a nascent crystal, and the stability can be described in terms of two terms. A bulk term that is favorable and an interfacial term which is unfavorable. This gives rise to a free energy barrier, and these thermal fluctuations that we would like to understand and study are what takes a system over the barrier. Now, this can be fairly complex, so simulation is ideal not to try to understand this type of beautiful fluctuations. So there are many possible pathways for the phenomenon, and also there can be multi-step mechanisms. For instance, in this case, say first densification and then the creation of order. And so this is what we would like to study. And we will use a series of techniques. One of them is what Michele pioneered with Jörg Beller in 2007, and what I will describe now in my own words. It's what I call ab initio atomistic machine learning. So here we consider some training set. We will solve the time-independent electronic Schrödinger equation in some approximation. We will compute observables, say as expectation values in the ground state. We can do this at the DFT level of theory or beyond. And we will compute multiple observables. If we use the potential energy, this leads to machine learning potentials, but I will also try to show some examples of learning dipoles, one-year centers, charges, magnetic moments. So this is the training set. Now we also have a model that, for the observables, we have a series of parameters that here called theta. I will use mostly neural networks to do this. We'll use descriptors to preserve the symmetries of the problems. In particular, I will rely heavily on the DeepMD formalism. So this is short range. We can learn global, local observables, scalars, vectors, tensors, and equivariant or invariant, whatever is appropriate. And in the training process, we simply have this the mean square error with respect to the reference. Okay, so this is one of the techniques that we shall use, I think presented in a fairly general fashion. The second technique that I will rely on is enhanced sampling, and I feel a bit like preaching to the choir in this sense, but it's the first talk, so to lay the basis for this. So in spite of the model that we choose, we'll always face the fact that many phenomena are rare events in this context. For crystal nucleation is one such example that we cannot study directly using molecular dynamics. And for this, among the many techniques that can be used, I will focus on the OPS, on the fly probability enhanced sampling. We will construct a bias potential as a function of some collective coordinates. And we will use a reweighted kernel density estimation to build the unbiased probability distribution. And from this, we will create the bias potential. Now, this really, the fact that OPS has many advantages. It's easy to use, fast convergence, easy reweighting, really, I think, means that it's now a very commonly used method. Okay, so this is a bit the introduction. Now I would like to show you a few examples of the things that we can do using this combination of techniques. The first one that we did was homogeneous ice nucleation together with Roberto Carr. I will mention that briefly. Then we went to something a bit more complex, heterogeneous ice nucleation on the mineral feldspar. I will also present some results on the precipitation of calcium carbonate that we did with Paolo Raiteri. And finally, the growth of magnetic materials, which is something that I've been focusing recently. Okay, let me check the time. Okay. So I went for a postdoc after doing my PhD with Michele, with Roberto, and a big focus there was understanding the properties of ab initio water and ice using the scan DFT functional. And this is the phase diagram computed using machine learning-driven molecular dynamics, in particular a DeepMD or deep potential model. You see here the comparison of this model with experiment, where qualitatively the results are good, but there is a quantitative difference between the coexistence curves in the experiment and ScanML. We then wanted to see how this model based on scan performed for the prediction of nucleation rates. And so we computed the nucleation rate as a function of supercooling. The results of the ScanML model based on the deep potential methodology are shown here in green, and you see the experiment in red. So the results are, overall very good. So there is a quantitative agreement in some regions, although at high supercoolings there are some discrepancies. Now, even though these results were satisfactory, I always thought that, the best classical or empirical models also give a very good agreement. So perhaps this was not the right problem not to tackle with this methodology. So the next thing that I focused on was the precipitation of calcium carbonate at near neutral pH. The reason, this is something that I've been doing with Eslam Ibrahim, a visiting PhD student at Nanocluster. The reason why I chose this is that at near neutral pH, the most common species solution is bicarbonate. Yet, we can still form at these conditions a carbonate-based crystal. So this means that there is, of course, a transformation of bicarbonate into carbonate during the crystallization process, and the mechanism for it is not fully understood. And furthermore, reactivity is key for this process, and these machine learning potentials are fully reactive. So we thus started to work on this topic together with Paolo Raiteri after a conference where we met. And so what we did was we constructed a training set that included, bulk water, bulk calcite, ions in solutions, the flat interface. And we started working with this. We trained a machine learning interatomic potential for this topic. We studied the properties of solutions and the solid. And what we found is that the ion pair association curves look like, what you see here in red. So this is, very close to the reference DFT value, but more importantly, significantly better than the rigid ion models. So within models that don't have polarization, you cannot really describe well the interaction between these calcium and carbonate ions. But much more importantly, we did simulations with reactivity. So what we studied was the carbonate to bicarbonate transformation during the association of the ions. So what we did here was an OPES, enhanced sampling simulation, in which we have the distance as a collective variable and the coordination of the oxygens in the carbonate with the protons, which sort of define that this is the carbonate and this is the bicarbonate. Now, very importantly, what we find is that the pathway for the conversion between the ions goes through the association. So association is key for the transformation of bicarbonate to carbonate. And this is already, say, hinting at the fact that during crystallization, aggregating will be crucial for allowing the carbonate to bicarbonate to carbonate transformation that we need. Okay, so then we went and we did a larger simulation of the initial stages of the precipitation of calcium carbonate with unconstrained reactivity. And what we find is that when we start from only bicarbonate, this quickly, as the system aggregates, you see the transformation from bicarbonate to carbonate quite fast, in the time scale of nanoseconds. And I think this is the first time this process could be simulated with full reactivity because we have these high quality and reactive potentials to do so. Okay. Something else that I wanted to check is that, well, of course, we have ions in solution, so electrostatics are very important. And for this, we constructed an ab initio machine learning model for the electrostatics. This is the deep potential long-range formalism put forward by Roberto and co-workers. And it works as follows. So, well, I said that one could learn different observables using atomistic machine learning. One-year centers are one such observable. So let's go through the formalism. Again, we start with a time-independent electronic Schrödinger equation. We can write the solutions using Bloch's theorem in terms of delocalized eigenstates, but also we can do one-yearization and write this in terms of one-year functions. Now, the one-year centers are these, the expectation value of the position operator in this one-year function. And we will, well, you see here, that this represents the center of the electronic charge. Now, when we have these one-year centers, or, well, we can also condense them into centroids, we can write an electrostatic energy where we have that charges are constant, but the one-year centers can move around. So this gives a polarization and charge conservation. But of course, large systems cannot be tackled directly in this way because, well, of the limitations of electronic structure calculations. So we train a model to predict the position of the one-year centers, as I described before. So this is the deep potential long-range formalism. We apply this to calcium carbonate to understand if, well, how important are long-range interactions in this system. So here you see the description that we have in terms of these one-year centroids and the, well, the positive charges at the nuclear coordinates. We do this for carbonate, for water, and for calcium. And what we find is that, well, when we compare the ion pair association curves, calculated also using enhanced sampling, with and without long-range interactions, we see that qualitatively they're not very different, but as we go to long distances, the short-range model goes to 0 at twice the cutoff because the interaction is mediated by water, but the long-range model correctly goes to the expected Coulomb interaction limit. And we can compute this difference in free energy between the two states, so that is non-associated and associated state. And what we find is that there is a sizable difference in this difference in free energy. So long-range interactions are important to capture the ab initio thermodynamics of this system, but in a quantitative way. In a qualitative way, this is actually not extremely important. Okay. I would like to talk about another project, which is the growth of magnetic 2D materials. This is something that I have been doing in collaboration with some colleagues in San Sebastian. Well, these are the students that carried out the work. So we will focus on the growth of this van der Waals layered material, cobalt dibromide on gold 111. So this, my colleagues came to me and mentioned the fact that there seems to be a precursor phase forming before this monolayer forms, and that, well, they find this precursor phase with this interesting motif. So what we did was we simulated the reactive deposition of molecules using the Mace MP foundation model. We validated it using a spin-polarized DFT calculations, and we found that the model was performing quite well, even without any fine-tuning or further training. So you see that the error was 150 milli-electron-volt per angstrom, which is quite reasonable. And well, these are the results of the simulations. So after we deposit some amount of molecules over the gold surface, you see the formation of these triangular patterns. And I'm showing here in detail how these are formed. Once that we had this structure, we actually did direct DFT calculations that bolster the evidence that this system grows via two-step mechanism. But since we had the reference DFT calculations, we decided also to build a machine learning model for the magnetic moment in order to be able to predict the magnetic moment in large systems. So during growth, being able to study how magnetism changes. So we built, I think, a quite reasonable model for cobalt, which is the magnetic atom here. And what you see in this movie is that as the cobalt dibromide molecules come and interact with the surface, really the environment modulates magnetism significantly, and this type of tool gives us the opportunity to understand how magnetism evolves and appears during the growth of magnetic materials. So I'm excited about this. I'm trying to understand a bit more how this changes when you go from the precursor phase to the final trilayer. Okay, so with that, I think I gave you a couple of examples of different quantities that one can learn and use to incorporate more physics into the simulation. So I mentioned learning not only the energy, but also magnetic moments and one-year centers to include electrostatic interactions. Okay, and something else that I would like to mention is the self-assembly from the gas phase, which is something that I find very interesting. So we consider a binary Lennard-Jones mixture, and we see that spontaneously these systems forms previously unreported patterns that we really cannot understand very well. These molecules are called according to the coordination number, and it really forms mysterious patterns. Let's have a look at what it forms. We really cannot understand it very well. If you have any idea of what this means, please do let me know. It's a fantastic example of self-assembly. And furthermore, you can notice that the colors are blue and white. So this is not surprising. These are the colors of Argentina. And something very important that I learned from Michele is to be proud of where I come from. And I come from Argentina. I would like, instead of describing conclusions, I would like to remember some key moments and phrases of my time with Michele. Probably you don't remember these, but I remember them very well. One of them is this one. So after we prepared our first manuscript together, we had a deadline. It was for a Faraday discussion. Michele said, "Can you come and we work on this on the weekend?" I said, "Sure, I would be glad to." And we're there working over the weekend. We finished the first version of the manuscript. Michele finishes reading the manuscript, looks at me and says, "Possiamo fare meglio." we can do better. This is embarrassing and it hurts a little bit, but I think then we went on to do more impactful work. But I think what I learned from this is the shared responsibility. Shared responsibility in doing great research, and I think we did manage to do excellent research together. So, possiamo fare meglio, the first one. Second one. So I had just arrived from Argentina to Lugano, and I guess I was thanking Michele all the time. You know, after our meetings, I thought, well, I'm working with this big boss. I mean, his time is very valuable. And I guess it bothered him so much that I was thanking him constantly that he said, Pablito, you don't need to thank me. We work together. But it's also something very important. I was not working for him. We're working together to do excellent science. And I think that's an excellent way to see things. So I am not sure what I said when I interviewed for the PhD position with Michele in 2004, but it was really a defining moment in my life and an enormous stroke of luck. So thank you, Michele, for teaching me how to do excellent science and so much more. I couldn't have had a better role model for supervision and mentorship. And well, I'm trying to follow in your footsteps, although it's challenging. Okay, so I thank many collaborators and funding sources. This is my small team in San Sebastian, which did some of the work that I presented here. And with that, I thank you for attention. I take questions, but before that, I leave you with some pictures of well, my time with Michele. Now, I don't take questions on barbecuing or cooking meat. That's top secret. Okay, that's it.
Thanks very much. But if you invite me for a barbecue, please, it will make me happy.
Well, we can talk about that.
All right, time for questions. Maybe I will start. Sorry.
So you presented many examples of system where there is a charge transfer happening. And can you comment on how, in your opinion, the validity of all these models for system where there is a charge transfer happening, and how you check, for example, that the charge transfer that is happening in this system is actually correct with your machine learning potentials?
Well, thank you for the question, Julia. In the case of calcium carbonate, when there is the proton transfer, the proton takes the charge with it. So the proton takes the charge with it, the electronic charge with it. So in that case, the formalism that I described has no issues in the sense that so you can always associate 1S centers to there. It's not an issue here. No, so you can always associate the 1S center to the oxygen, to the proton, and there's to the oxygens, and there's no problem with that. No, sorry, on the contrary. So when there's the proton transfer, it leaves the charge behind, and it's connected to the oxygen. So there's no problem with that. That works well. In the case of well, this is for, when we're dealing with long-range interactions. In other cases, I understand that there will be charge transfer, and this formalism cannot work like this. It has to be modified, and I think maybe you will talk about that, Roberto. Not really. Okay. So Roberto is working on extending that, but it is a limitation in the formulation that I used. If there is charge transfer, we cannot model it in this way. But for this system, it's correct.
Yeah, thanks, Pablo. Really, really cool stuff. I actually have a related question to Julia's. So in this case of calcium carbonate, so you said you see this proton transfer and the formation of the bicarbonate product. I guess, could you check with the pKa calculation if that's if the thermodynamics checks out and if your results are comparable with the pKa values?
Yes. Thank you for the question. We indeed we are not say, computing what the pKa values are for the ab initio model, but I don't think that affects the conclusions of this part, no, or better, of this part, which is the role of the association in the proton transfer. No, but indeed, in a longer study, I would definitely go for the calculation of the pKa, and it's of course important. Yeah, I agree.
All right, thanks.
More questions? Yes.
Thank you so much. My name is Boyega Adebayo, and I'm from Nigeria. Well, my question is one, but I want to make a comment with respect to what Ali Hassan-Ali has said. For some of us from Africa, actually, we are truly, science is actually lagging behind. The ICTP and the scientists here, people like Professor Erioto Sati, Sandro, yeah, they have actually contributed a lot to bringing science in Africa up to where we can actually say, yes, ICTP has contributed a lot. So I would like to say thanks so much for all of them for actually organizing activities like this. Because one thing that has helped us is the fact that we have direct contact with the people who are actually doing the science. So it's a way to actually learn and also do good science. So my question actually is on how do we start a process of training, let's say, Parrinello MD for a system. What are the process for the machine learning? Thank you.
Which part in particular you're asking about?
For example, if I have a crystalline system,
yes,
and I want to perform a machine learning using the Parrinello model, how do we go about that?
Okay, so yes, I mean the process of creating an initial training set. You mean for training a model for?
I guess for your specific case of crystallization, how did you manage to build this neural network potential from ab initio?
Okay, I think there's no unique way to do so. The one that I did in this case, and I think was successful, is using a bit of intuition regarding what could be relevant in this system. In this case, it seemed a bit natural to me that these were the essential ingredients that one would need. So bulk, we're studying crystallization from solution, so having the solutions and the bulk solid and the interfaces seem to me to be the most important things. Now, this is the starting point, but then when you do the simulation itself, will suggest new configurations that you can add to the training set. So I would say a guess, and then adding configurations from the simulations itself. Although the landscape of this is changing, and fine-tuning is becoming more and more common, where you start from pre-trained models.
All right. If there are no more questions, I would like to thank Pablo again. Unified representation, learning, and sampling. Unification, yes. Stage is yours. Let me see if this thing is working. I will warn you after 20 minutes if necessary. Yeah. All right. All right.
Is how do we model complex molecular systems, right? And one unifying theme across these different molecular systems, which perhaps allows us to jump from proteins to DNA to RNA to crystals, is in the end they're atoms moving on some potential energy landscape, right? It's very rugged, it's got a lot of transition states, and that's it. But while force fields, of course, look at the potential energy landscape, we are very well accustomed in science to be thinking about low-dimensional representations, and these low-dimensional representations change from system to system. For proteins, like on the bottom left, you would think about an energy landscape in terms of a representation where you have a sharp funnel, maybe your representation in the terms of some native contacts or something like that. For RNA, maybe Giovanni Bussi will probably tell us later what's a good representation think for RNA. For crystals, like Pablo showed, it's really messy. It combines the worst of everything. If you form a perfect crystal, it looks like a protein. If you get stuck somewhere else, it looks like an RNA. So while everything indeed moves on a high dimensional energy landscape, our ability to understand complex systems comes from how we represent them. And not just understand them, also sample them. If we don't have these low dimensional representations, often we are stuck in whatever basin we started in the potential energy landscape. So, and when I was working with Michele around, I left in 2015, back then we had not really started as a community very carefully thinking about how to optimize collective variables on the fly. The attitude was you take a collective variable, do your sampling, you like it, everyone else criticizes you. Why did you take this collective variable, right? This was for metadynamics, for umbrella sampling, every method, this was the story. And one of the themes that really started emerging around that time and was that we can think about collective variables on the fly. We can use our sampling to learn better collective variables. And secondly, these collective variables will have to do something with dynamics. It's not going to be only structural perspective. So one of the other gifts you gave to me, Michele, was to pack me off to Bruce Byrne after a postdoc with you. Michele said, you are interested in collective variables, you have to think about dynamics, and I can't think of anyone else better than Bruce Byrne who will tell you about dynamics. Now, Bruce's group was very different from Michele. There was no one, just Bruce and me. But that was another story. So we had a great time, and that's around 2016 when I was a postdoc with Bruce, I came up with this method called spectral gap optimization of order parameters. Around the same time, Michele started working on similar methods. I remember there were two preprints out there, one by Michele called MetaTika, and the other one by Vijay Pandey called Tika Meta, and in parallel, and maybe the names change. And so the community has come up with a lot of methods on how to use dynamics, some amount of dynamics to come up with better collective variables. Today, I will be talking a little about the method from my group called state predictive information bottleneck. So while this is how we can learn low dimensional representation, in parallel, we still have the sampling challenge. So what do I mean by the sampling challenge? At heart, it is very simple. You have a force field, U of x, like the force field Pablo showed you in the talk before, and the force field is given, and the sampling challenge simply means, given force field U of x, where x is high dimensional, it's in R3 space, generate an ensemble of points, time series, or just an ensemble of possible x values which are physically relevant from within the states, from the metastable states, from the barriers. So that's the sampling challenge, simply stated. Now, in the last 10 years, we also have the generative sampling challenge, which is sort of similar, but not quite. Generative sampling challenge says that, okay, maybe you have U of x. Maybe you consider it, maybe you don't consider it. But the problem is as follows. Given samples of x, instead of knowing what is U of x, if you had generated some samples of x, can you generate me other samples of x, which would have come from this underlying probability distribution? It is possible that you have at your, for your x's, this U of x, that you can use it, or maybe you don't use it. And the classes of generative sampling methods can roughly be classified as per this separation, where they use U of x or not. The class of methods that became very popular starting around 2019, even though some of the ideas have existed for a long time before that, is Boltzmann generator or normalizing flows, where the idea is you use U of x, which is coming from a complicated probability distribution, you transfer it into something else from which you can sample, and then you transfer it back. The mapping has to be invertible, and for this you need to know U of x. Without using U of x, the class of methods that is most popular is something known as diffusion models. They really started picking up around 3 years ago. My group has been working on it since a bit before then, so it's very interesting to see how they're really taking up a lot of interest from the community. And the class of methods here, which does not use U of x, is called thermodynamic maps. And while in today's talk, I don't want to talk about these methods, in the spirit of what Ali said, Abdus Salam saying theory is cheap, anyone can do it, I will show you some basic methods, some basic ideas, nothing too fancy, so it's going to be a simple talk. I do want to show you one result about why these type of methods make you almost feel that you don't need to know anything about low-dimensional collective variables. So this thermodynamic maps method, which we published first in this paper in PNAS, but if you really want to read only one paper, you should read the middle one, and then PRL just came out a few weeks ago. And I will show you this one result, which I like quite a lot. I'm biased, of course, where we look at everyone's favorite model, the Ising model, right? For Ising model, let's say, and this is a simple nearest neighbor interaction Ising model on a square lattice. On Sagar calculated the critical temperature for it, 2 divided by natural log of 1 plus square root of 2. We know the critical temperature. But let's say we have lots of samples of this Ising model deep within the one state and a bunch of samples in the other state, nothing close to the boundary. And we take these bunch of samples, I'm not showing only one sample each, bunch of samples, all spin configurations, no dimensionality reduction, and I ask an AI model to come up with magnetization in between the two temperatures. Furthermore, even come up with the heat capacity and how it spikes during the phase transition. And this method that I'm not going to be talking about, thermodynamic maps, can actually do that. It can even get the critical exponents, apples compared to apples. We are not for, it should of course diverge in the thermodynamic limit, but when you do Wang-Landau, you will get the same critical exponent. So these type of methods are powerful, and you don't need to do any dimensionality reduction. It would almost make you feel like collective variables are dead. Like, what's the point in doing it? And I was thinking, what should be the birth date for collective variables? Should it be 19 something? No, but collective variables are fundamental to thermodynamics itself from the time of Gibbs. When we think about an ensemble, what are the natural variables, right? This is at the heart of thermodynamics. Is it NVE? Is it NVT? Is it something else? What do we use to represent a system? So no, it's not so easy, because even though I showed you these results on diffusion models, the reality is as follows. So here I am showing you 3 classes of generative AI models: normalizing splines, which is normalizing flow, conditional flow matching, and diffusion models. And this is a very well curated system where I have only 4 states, but what I do is to increase the dimensionality. And look at the error in the generative AI model. As the dimensionality increases, all generative AI models, the error just blows up. And then it starts to converge for some of the methods. For normalizing flow, it actually continues to blow up. For other methods, it converges. The reason why you should use normalizing flow still is because it's much faster than these other methods. So there is a lot of nuance in these methods, right? You cannot just use it. You might be thinking that you are good results, but the error might be very high. And on the right side, I'm showing you an even more basic perspective, which comes from basic statistics, is if you have some ground truth f hat and you're trying to fit a model f, and if the dimensionality increases, the number of data points that you need to have to get to the same error R increases exponentially. So yes, we can keep generating more data to train our models, but if we do it in very high dimensional space, the amount of data we will need, we will end up trying to catch with it for no reason. So it's useful to think about dimensionality reduction. So how do people do it in generative AI? Well, AlphaFold 3 uses diffusion model in all protein space, which is tour de force. It's incredible that they can do that. But they also have a lot of GPUs, and it's expensive. It's not very easy when they did the training and everything. The fast models, when, for example, this is one of the most popular generative AI models using diffusion called stable diffusion. It was, I think, related to the early forms of DALI and things like that. Here, people do not do diffusion in the space of all pixels in the image. They take the image, they compress it using an autoencoder into some low-dimensional latent variable, and then they do diffusion in the space of this low-dimensional latent variable and bring back the image. So the same problem that we have been seeing in metadynamics for the longest time, collective variables, same things happen here also. You have to train an autoencoder. And for images, you can do that because, well, the internet is full of images. For rare events, how do we do that when we haven't seen what's going to happen? How do we go and pre-train such an autoencoder, right? So we have to have a unified discovery perspective where, number one, we need dimensionality reduction because otherwise we will just need too much data, our method will be slow. Number two, we don't know how to do dimensionality reduction because we don't have the data to train these models on. So in the next 10 minutes, I will quickly give you a flavor for how my group has been thinking on these problems. I'm not the only one to think in this direction. A lot of people in this group are also thinking in this direction. So, with that caveat, the first class of methods that I will talk about is as simple as just iterating between rounds of metadynamics and learning this information bottleneck until the answer converges. In the language of machine learning, this is not end-to-end differentiable. It's kind of clunky. It's basically doing metadynamics with some chosen collective variable, looking at your sampling, retraining a new collective variable, doing it a few times until the answer, the landscape, qualitatively or quantitatively, does not change, right? That's what this method is. The second one, which is still a preprint, does both of these things on the fly together. So for this, one of the things I would hope that you take away from this talk is this notion of an information bottleneck, especially state predictive information bottleneck. So the idea of information bottleneck goes back to Shannon in the 1950s when he was interested in how to compress signals so that they can be recovered on the other side without the whole signal being out there, right? So you were trying to transfer codes. And then Bill Bialek, who I believe has also spent a lot of time at ICTP, really popularized it 2 decades ago with this notion of information bottleneck. Bill Bialek said, and that's the version I'm going to use today, but the change that I have over Bialek's formulation is this notion of state predictive information bottleneck. So we are trying to do information bottleneck for molecular systems which we know have metastability. So it won't work for glasses, but be it an RNA, be it a protein, be it a DNA, be it a crystal, it does get trapped in metastable states. We don't know how many metastable states, we don't know how they look, we don't know where they are, but we can agree upon that there is some sort of a timescale separation. We don't know how many fast timescales, we don't know how many slow timescales, but metastability exists. So with this, what we do is to take something that looks like an autoencoder, but it's not quite an autoencoder. So I have some high-dimensional input of some biological system or a material system. I will compress it into a bottleneck variable and try to decode it, but instead of trying to regurgitate everything that I put into the model, all I will try to recapture is the future state of the system. So the prediction task is much easier now. Okay, so what I'm saying is, if you want to say whether I'm standing here or whether I'm sitting in this chair, do you really care about every single hydrogen atom in my body? If you're Ali, maybe you do, because he's very interested in hydrogen and things like that. But probably you don't. Probably you just want to classify, right? Whether it's this state or that state, right? Second thing, how many states does a condensed matter system have? There is no quick answer. In protein folding, people always fight over it's a two-state folder or a multi-state folder. To some extent, the question is absurd, because if your time resolution is picoseconds, then of course it is going to have many more than 2 states. If your time resolution is hours, then it might be a 1-state folder, right? All you will get is the stationary state of the system. So the number of states of the system is going to depend on this time lag parameter, delta t. How far into the future you are trying to predict. And then in the style of Bialek, we have a difference of 2 mutual information. What you're trying to do is to minimize the mutual information between the input and the bottleneck, and you're trying to maximize the mutual information between the bottleneck and the output. Since we don't know the number of states a priori, we take a mixture of Gaussian priors for the latent variable. Normally in autoencoders, people take a single Gaussian prior. Here we take a mixture of Gaussians, where by iterating through this process in a self-consistent manner, in a fully automatic manner, you can learn the number of states the system has. So for example, if you have a 4-state system, you don't know how many states exist initially, so you say, let's say I have 10 states. And you try to go through this, and the population of these 10 states will disappear, and you will be left with 4 states for a certain lag time delta t. If you made this lag time slower, then this barrier over here will become irrelevant, right? It is too fast relative to that barrier, and you will not be left with 4 states, you will be left with 2 states. We can look at a system that many people in this room have studied before, including, I think, Christoph has papers on this, is ion pair dissociation in water. So what's the reaction coordinate for this process? Naively, you would think it's the distance between the 2 ions, right? But the waters have to move. So for this one also, we start with initially assuming 10 states, where coordinate 1 is, and the input features are much higher than just 2 coordinates. But for the sake of projection, I'm showing like this. And depending on how far into the future you're predicting, if you're predicting, let's say, 8 picoseconds into the future, you are just left with bound state and unbound state. If you're predicting 0.4 picoseconds into the future, you have this so-called de-wetting type transition, the same transition that Bruce and David Chandler and many others worked on over the years. So this information bottleneck gives us that, and furthermore, when we finish the information bottleneck training, we get the 50% committer surface. So here on the left, I'm showing you work that I actually did with my colleague John Weeks. And there is another story here, like how much long-range interaction do you really need to get that 50% committer? And for John, it was quite disappointing. Was it disappointing? No, he was quite happy because, right, for WCA reasons. You did not really need the long-range interaction. You could get that for 2 ions, but that's not relevant to today. What I'm trying to show here is the bottleneck gives you the 50% committer surface, which if you go and compare with, for example, very accurate likelihood maximization calculation, which is more expensive in this case, you get the same 50% committer surface. So this means we can use this committer, this approximation to committer, because committer itself is very expensive to calculate. This bottleneck can be calculated cheaply. It can be even calculated from bias data. So in this RAVE method, what we do is we start with a round of sampling. We learn an information bottleneck. Notice here I'm showing a linear encoder. Number one, if the initial data is not good quality, why do you want to use a nonlinear encoder already? It will overfit things. Number two, linear encoders are easier to interpret, so we start with the linear encoder as long as we can keep it. And we iterate. I, of course, trained with Michele, so I started by doing metadynamics. Soon enough, grant reviewers started making noise. Why are you using metadynamics? Use other enhanced sampling methods. Metadynamics is still my favorite. It's clear when you use these other methods how metadynamics tends to be self-diagnostic. When the simulation gets trapped somewhere, you can see that it's not working out. As opposed to umbrella sampling, you can diagnose it, but you will have to be very careful to do that diagnosis. In metadynamics, it will scream to you like, don't trust this trajectory. In the next part of this talk, so far I showed you this RAVE method where we do metadynamics, we learn an information bottleneck, we keep iterating. 5 minutes? Okay, great, perfect. We can go one step further. We can say, well, it's still clunky, right? You have to do two things separately. Can you combine everything? So for this, we take a step back and look at normalizing flow. And if you want to read about this paper, the preprint is out on archive. So for normalizing flow, what do? We have some features. We transfer it into some latent space where we have a simple prior, where we can draw lots of samples, and we come back and forth. However, in normalizing flow, the input features tend to be the all-atom coordinates, because you do need the U of x. You need the full potential energy. If you did not have all-atom coordinates, the U of x will have to be replaced by F of x, the free energy. And that's, again, the chicken versus egg thing. You don't know that. But we can combine this nicely with our state predictive information bottleneck. You can also think of it as replacing the Gaussian prior, the mixture of Gaussian priors with a normalizing flow prior. So now all of this works together. We are learning the information bottleneck. We are doing normalizing flow on it. It comes and tells us the number of states. It goes back, and everything works fully automatically. And we can do many, many things with it. For example, I'm going to show this. This one is simple but quite interesting. So one of the things we teach in StatMech is that high-dimensional spheres are funky, right? Most of the volume of a high-dimensional sphere lies on the surface of the sphere. So if you're doing your prior in normalizing flow, which is in high dimensions, and you take a Gaussian, if you take a simple Gaussian, all your weight is going to be concentrated on the origin. That's not the smartest thing to do, because there is not a lot of volume in high dimensions at the origin. It's really at the surface. So what we do here is to stretch out the Gaussian. So it's sort of like a Mexican hat. So we don't keep it at the middle, we stretch it out. If you stretch it out, suddenly you have so much volume. And other thing that happens with it is that as you stretch it out, the amount of stretching can now correspond to the temperature at which you ran your simulation. And suddenly we come up with something very powerful. We can now do generative AI at 2 temperatures, combine it to generate data at any other temperature of interest. And that works out quite nicely. And it's important, of course, for a lot of systems. So here I'm showing you some protein. What is this? Chignolin, something. Where I do simulations at 340 Kelvin, 440 Kelvin, and I have folded, misfolded, and unfolded state. And I can generate, in the bottom plot, you can see these violin plots, the ensemble of RMSD distribution at any other temperature. You can even extrapolate across the temperature range, even though we never did simulations at those temperatures. And my group has become very interested in RNA, where things are very intriguing for a variety of reasons. These things also work for RNA. Like I said, I didn't want to go too much into applications in today's talk, but we are doing a lot of practical things with this. So I can summarize at this point. In enhanced sampling, we have been thinking for a while about how to pick collective variables, right? How to think about them. And I think the same issues apply in generative AI. Otherwise, you will be just burning through your GPUs. If you're not doing dimensionality reduction in a smart way, probably on the fly, and thinking about your system, it's a misuse of GPU resources. While we have a lot of GPUs, we should still be efficient about those things. And today, I discussed 2 methods briefly. The RAVE method, which learns an information bottleneck, iterates between metadynamics, and then later I showed you this latent thermodynamic flow, where I mix the information bottleneck with normalizing flow. And we have some work that we have not published yet, where we replace it with diffusion flow. and there are even more powers that come out. With that, I would like to thank you for your attention, and I will be happy birthday, Michele, once again, and I'm happy to have any more questions.
Questions?
Hi. So I was wondering, when you show these different states and all these methods and so on, what is the largest system that you can simulate, like protein complexes or hundreds of
We have gone to CAR-T cells now, which are like disordered proteins, 500,000 atoms and things like that, big ones.
So I don't see raised hand. Yes, at the bottom. They have a question.
Thank you so much. Now, the U of X, what actually happens if it's periodic or non-linear?
So most of these simulations are in periodic boundary conditions, and I don't think that is an issue as long as your molecular dynamics engine can deal with it. So that's not an issue, generally speaking, but it's good to be careful about that.
So maybe I have a quick question myself. So imagine that you do, so you take a piece of trajectory and you do Markov state modeling, even if it's not at convergence, and you use this Markov state modeling to do your...
It's not exactly Markov state modeling.
I know,
yeah.
But what is the... So I know it's not Markov state modeling. This is absolutely clear to me, but I was actually wondering if what you're doing is a sort of smart version of doing what I said.
It might be. So we tried to do Markov state modeling. In fact, we compared it with Markov state models, and we found is if you do naive Markov state modeling, the lag time that you need to have for the eigenvectors to converge is too high.
Yeah, this is too high, but doesn't it also provide you a guideline for optimizing on the fly your manner of representing the data, finding the microstates? So I see some flavor.
That's a very good point. So in principle, and people have perhaps tried to do that, right? There's rounds of Markov state modeling. But the problem, of course, is where did the initial data come from, right? So one of the things you are doing in this framework is that the initial data can come from biased trajectories, and that makes it a bit faster. But you're correct in your comment.
All right. More questions? Yes, Nikhil.
So going back to the Ising model is very challenging. So what did you get for the critical exponents?
I have the numbers right here. So there are two critical exponents, right? So this one I'm showing you for the heat capacity, but that was around 0.25, which is what you get for this system size from Monte Carlo. Remember that if you did to thermodynamic limit, it would diverge. But we want to compare apples with apples. So you get what you get from Wang Landau in this case, much longer Wang Landau.
So how is your machinery able to recognize that this is a second order phase?
Oh, this one is magic. This paper is awesome. We can talk about it more later.
Okay, mystery, magic. Okay, great. Thanks. More questions? If not, we thank Pratyush again. Next speaker is Michele Ceriotti, who will tell us about simulation recipes from the Parrinello family cookbook. Fantastic.
Thank you. So, for example, Michele has done so many fantastic techniques based just on the idea of building an extended Lagrangian. And this really, you need to understand, not everybody does rational mechanics as an undergraduate anymore. And instead, I think there is a lot to gain from having a very good understanding of the fundamentals. The second lesson is not to be afraid of doing complicated stuff. Not do complicated stuff for the sake of it, but if you need to do something complicated, then just go and do it. And I don't know how. I think it's very dangerous when Gareth Rebello and I work together. But reconnaissance metadynamics is the first example, and the second example is something that we called field overlap metadynamics, which was a method that was so complicated that it had something that we called stargates. Okay? But, sometimes you need complicated stuff to achieve your goal. And the last Parrinello lesson about doing simulations and doing method developments in simulations is that it's very important not to just have the idea, but also go all the way to implement it in a way that makes sure that other people can use it. And so, with this spirit, in an ever more complicated world, in which if you want to do simulations, you need to understand statistical mechanics, quantum mechanics, and now also machine learning. And in a world in which, Fortran 77 is not enough anymore, but you need to know about TensorFlow, and then PyTorch, and then JAX, and every 5 days Meta pushes out a new version that breaks everything that you have been doing. So, you have to deal with all of these different pieces of software. It becomes extremely important to have a book of recipes that tells you how to use all of these techniques. So over the past year or so, I have been devoting a probably inordinate and excessive amount of time to putting together this website, which is called the Atomistic Cookbook, that contains recipes for performing simulations. And so I thought that today I would pick two of these that, in my opinion, embody very well the Parrinello style. So before I do this, I also need to do sort of a prologue, because I will be using a lot a universal machine learning potential, which is called PETMAD, which is something that we have been developing in my group, and you will hear a little bit about the architecture and the model structure, but one particular feature of this model is trained on relatively little amount of data. So you are going to hear that you need hundreds of billions of configurations in order to train a machine learning potential that can work across the periodic table. Well, everything that I'm going to show you was trained on a model that used only 100,000 structures. And I think that this is very important. And I mean, this is a plot of the accuracy of the model on an external data set as a function of the size of the training set. And you see that, the fancy pants models from Meta use 100 million configurations, but, we get close enough with 1,000 times fewer structures, which I think is very important for usability. This is, and when you look at the performance, actually, if you look outside of the family of data sets that these huge models are trained on, it turns out that this small, humble model performs actually better. And it's also very fast thanks to an architecture that is not constrained to being rotationally equivariant. And I'm going to get back to that. But now, let's look to a couple of these recipes. And the first recipe that I want to talk about is actually a recipe about errors. Because, there's so much choice about how to build your machine learning model, your machine learning potential, but can you trust it? I can't sleep well unless I know how reliable is the model that I am using. And if you start asking yourself how to estimate the error in a machine learning model, well, there are many, many, many different possible choices. And so we worked quite a bit on this topic. And so after considering all of the possibilities, we converged on a set of choices that we think work very, very well, which we called this set of choices direct propagation of shallow ensembles. So the idea is that this is an architecture for the error estimation which is based on ensembles, meaning that your model will not output just one value of the energy and the forces, but will output like 32 different estimates. And then you will take the mean as your best estimate of the potential, and the standard deviation of these 32 estimates as your uncertainty. And now these, if you do it naively, will make your estimation 32 times more expensive, but actually we find that it is possible to have just the very last layer in the model different between the 32 predictions, which means that the vast majority of the computational effort is shared, and so basically you get these 32 estimates at the cost of one. And I'm going to tell you a lot about this in a second, but what is very nice from this ensemble architecture is that if you want to do something with this prediction and not just quote a number in a benchmark table, well, what you can do is simply apply your complicated simulation workflow to each of the outputs, and this will give you an ensemble of predictions that have been propagated across the workflow. But first, I want to sort of kind of convince you. I don't know how much this single figure can convince you, but you know, essentially a good uncertainty estimation model should tell you that the actual error in your simulation, which is the y-axis here, is large when the predicted error on the x-axis is large. And for all of these different examples, this is the case, and you know, the fact that you have some cases in which the actual error is very small is actually not a problem, because you should have a Gaussian distribution, and in any point the most likely error is 0. But what I want to stress is this idea of uncertainty propagation, which is extremely important. Because I give you here a very simple example. You want to compute a vacancy formation energy. You run your machine learning potential on a bulk structure, you compute the energy, and the error is about 1 eV, because it's a large structure, so the total error is large. And then you compute the energy for the relaxed vacancy, and the error is another eV. And the vacancy formation energy is 0.7 eV. So you can't trust this number. Well, actually, no, because there will be a huge amount of error cancellation because you're subtracting one energy from the other. And doing this with ensembles allows you to estimate that the actual error on the vacancy formation energy is just 0.1 eV. So, you know, good enough, and you know how large is the error. And this works in many, many examples. You can also, for example, compute many models of polarizability, do Raman spectra by doing the time correlation function of the polarizability along the trajectory, and you just do this 32 times with the 32 estimates of the polarizability, and you get an ensemble of spectra. And so at each point of the spectrum, you know how large is the error of your machine learning model. And so, for example, you can train a model of the form 1 of paracetamol and check if your prediction is still reliable for paracetamol form 2. But what if your workflow is running a complicated enhanced sampling technique to compute something like a melting point? Well, then what you can do is you don't have to run many different simulations for with each member of the ensemble. You can just run one simulation with the mean potential, and then you do thermodynamic weighting to estimate the thermodynamic properties that you would have had if you had run with each of the members of the ensemble. But you will tell me, well, what if the members of the ensemble are too different from the mean? Then you will get garbage. And that is true, but since we are not interested in a precise number, but we are interested in estimating an error, what you can do is apply a cumulant expansion technique to get an estimate that is statistically robust, even though it's not exact. And by doing this, getting back to the SPETMAD universal potential, you can do simulations with interface spinning and compute the melting point of gallium arsenide, and you get a melting point of about 1100 Kelvin. Now, this is not very good compared to experiment. It's about 1500 Kelvin, the melting point of gallium arsenide. So is this the fault of the machine learning model, or is it the fault of the DFT that this is trained on? So one thing that you can do to test this, I mean, running the DFT for doing the melting point of gallium arsenide is out of question. You need large boxes, it's too expensive. But you can train a bespoke model just for gallium arsenide. The error, of course, will be far, far smaller than if you consider a potential that can do the whole periodic table. And you see that it's the fault of DFT. You can also do fine-tuning that Pratyush has mentioned, that Pablo has mentioned, actually, and it confirms that really this is the accuracy that you can expect with the reference DFT. But you don't want to have to do this, if you have to do an ad hoc potential fitting, then what's the point of a universal potential? Well, what you can do is apply this ensemble propagation technique, and this technique will, from a single trajectory, will give you this bundle of predictions that basically tells you that the reliability of the universal potential is about plus minus 50 Kelvin, which is actually the correct order of magnitude of the accuracy of this model. So now let me get on with another recipe from the cookbook, which is about doing MD with direct force prediction. So what is this about? Well, those of you who know me know that I have spent like 5 years of my life and the lives of several PhD students understanding the importance of symmetry in the construction of machine learning models. And so, this very systematic study of the symmetry in different models came up with this complicated formulation, very general, that shows that pretty much all of the equivariant models share a structure in which you have density expansion coefficients combined with a sequence of Clebsch-Gordon products. And this is really the architecture that underlies all of the equivariant neural networks, as well as the, the original machine learning techniques, such as Beller-Parrinello neural networks, were based on a formalism that is equivalent to considering just these terms in the expansion and then throwing them in a generic convolutional neural network. So after spending a lot of time on this, I actually, allowed a PhD student of mine who really wanted to try something else to actually build a model that doesn't care at all about all of these, just takes the Cartesian coordinates of the atoms and throws them into a transformer and gets a prediction for the energy and the forces. And then how does it get to be equivariant? Well, it just learns to be equivariant by augmenting the data set with many different rotated copies of your data and just learning that the energy doesn't change when you rotate a molecule. So to my surprise and also to a certain disappointment, this works pretty well. So you get models that are as accurate or more accurate, I mean, as I showed you with PetMed, than equivariant architectures. And it's also, so basically, after all this time, spending my time thinking about Clebsch-Gordon coefficients and symmetry, I have to come to terms with the fact that maybe the best thing to do is just let the model learn the physical symmetries. Now, of course, having been trained by Michele, I have a healthy dose of respect for symmetry and physics, and I also know all of these horror stories about, this is a paper in which, due to error accumulation for compiling GROMACS in single precision, they started having water flow preferentially in one direction, and they got a paper published about it. So you never want to be on a slide like this. And so we started basically trying to assess carefully how accurate the model, how equivariant the model really was. So the idea is basically that rather than doing a single prediction of this point edge transformer architecture, what we do is that we at inference time, we average over a grid, a Lebedev grid of rotations. And so you can make the model without changing the architecture, without changing anything, you can make it as accurate in being equivariant as you wish. And so the long story short is that you do this and you look at pair correlation function, and there is absolutely no difference if you do the learned equivariance or enforced equivariance simulation. You do also, orientation correlation functions that you might expect to be more sensitive to rotations. Absolutely no difference. You look at dynamics, no difference. And so eventually, also after having figured out a couple of inexpensive way of making the model actually equivariant, I convinced myself that despite all the effort that I had put into understanding the architecture of equivariant models, maybe you can get away with murder and just let the models learn equivariance. And so this led me to consider a little bit more seriously a trend that had been growing in the community, at least in the computer science community, which was to compute forces for a potential, but not like any self-respecting simulator would do as the derivative of a potential, but directly as the output of the model. So the model doesn't compute just a potential that you then differentiate to get the forces, but the model directly spits out the forces as vectors. And the reason why people have been doing this is that this is about 3 times faster because the backpropagation has a cost, and by directly outputting the forces, you save about a factor of 3. So we implemented this, and it works in the sense that it is faster. So if you recall the plot that I showed before about the speed of PETMAD, there was a model, orb, that was faster, and this is a model that is that does this direct force prediction. And if we do the same trick with the PETMAD architecture, we get the same factor of 3 speed up. However, if you try to do MD using these direct forces, you get garbage. Unsurprisingly, it's not only that the forces are not the derivatives of the potential that you're predicting, the forces are not the derivative of any potential. They are non-conservative, meaning that the Jacobian is not symmetric, you get all sorts of horrible things, and you get a temperature drift of about 7,000 billion Kelvin per second. So when you think of this, this seems relatively benign, but when you convert it in actually human units, this is freaking insane. So, of course, people who are running these simulations don't do constant energy trajectories. And I just wanted to say this is not specific of our implementation. Pretty much any model that does direct force predictions will suffer of this problem, which is perhaps not too surprising. But, you just stick a thermostat on top of it, actually the Bussi thermostat, which also keeps the dynamics working very nice, and the temperature, everything is fine. Well, not really. If you look separately at the temperatures of oxygen and hydrogen atoms, you see that they are 60 Kelvin apart. And so the first message here is don't use direct force predictions. However, maybe, if you do things just a little bit more complicated, Parrinello style, there is a good way of using direct forces. And the point is that if you are predicting a potential, which you can do for cheap because it's just a different head from the same architecture, at any point you need it, you can also do backpropagation and get good, decent, conservative forces. And so what you can do is use both. So you can start, for example, pre-training your model using direct forces, which is 3 times faster than doing backpropagation. And after a while, you basically switch on the conservative heads, and this is in terms of total computer time spent, and now GPUs are very expensive, so you are really saving money here. You basically get to an accuracy that is the same that you would have obtained if you had run conservative forces all along. But also when you do MD, and this again, maybe it's not as much as a classic as an extended Lagrangian idea, but RESPA from Mark Tuckerman 1992 is this technique to do multiple time stepping. So you basically use a cheap force with a fast time step that is required by molecular motion, and then you correct every few steps using an expensive prediction. So here, cheap is the non-conservative force, 3 times more expensive is the conservative force. So if you do this, basically, you can evaluate the conservative forces only every 8 steps, which basically makes the overhead completely negligible, and you recover trajectories that you can run for as long as you want with NVE, and everything works fine. And these really work fine, not only when you do simple ad hoc tests. We just took this BMIM-CL, which is an ionic liquid, run simulations. If you run with direct forces, temperature explodes. If you add a thermostat, you can fix it, but then actually your chlorine ions equilibrate at 2000 Kelvin. Instead, you use this multiple time stepping idea, and everything works well. You get the right diffusion coefficient, right per correlation function, and your simulation is still effectively 3 times faster. So the PhD student who did this, Filippo Bigi, at that point thought, okay, can we do something even more crazy? And basically, he thought, okay, so if we can basically avoid doing the backpropagation and we just compute the force, now if you think about velocity Verlet, computing the force is equivalent to basically computing delta P. And so can't we just take Q and P at time t and predict Q and P at a later time in the future? And so Filippo put together an architecture to do this, which is just a slightly remodeled version of this point edge transformer. And he trained it on 100,000 trajectories, 100,000 NV trajectories generated with this universal machine learning potential, and came up with a universal model that can do this trajectory extrapolation and get you effectively molecular dynamics with time steps between 16 and 64 femtoseconds. And this is, I would say use it with care, because just as non-conservative forces, you don't, this is not symplectic. Now we have something in the making that is symplectic, but still a work in progress. Still, if you want to get a semi-quantitative idea of what your system is doing, this works very well. So you can do simulations of diffusion in lithium thiophosphates using time steps of 16 femtoseconds. You can do alanine dipeptide in water, and you can push it to 16 femtoseconds. You can do the surface permelting of aluminum 110, where you have this very subtle behavior of the atoms at the surface, and you can push it to 64 femtoseconds. So I'm quite excited about this, because, if you have something which requires a long simulation time, and you can, this is not a factor of 3, this is like a factor of 100, and so maybe I can be a little bit more willing to run the risk of having something which is not exactly symplectic. And, if you want to try it, there is actually a recipe for it. So it's actually very easy to give it a go. And let me know if it breaks your simulations horribly. And so with this, I wanted to conclude, thank all the people who did the hard work. And I can say that, I only hope that the members of my lab, will form such a, nice group as the alumni of Michele, who always keeps the time in Lugano or wherever you had the fortune of encountering Michele in their heart. And, just to give you an idea of how much we all kept Michele in our heart, when Gareth, Ali, and I climbed Kilimanjaro, we were on the top, oxygen deprived, and we had sign that reads RGP, Research Group Parrinello. So to the top of Africa, at least, if not of the world, we are really bringing you with us. So thank you, and thanks everybody for listening.
Questions?
Very nice, Michele. I was fascinated by this ultra long time step dynamics. I'm quite convinced you get very good sampling. How about so you're showing some kinetics here.
Yeah. It's okay-ish.
It's okay-ish. Can you
the,
comment a little more about that? Yes.
Yeah. So it's actually very interesting because, of course, these can't work indefinitely, right? You get Lyapunov instabilities, and eventually the trajectory becomes chaotic, and no amount of machine learning can learn chaos. But there is this intermediate regime where it works pretty well, and the main issue that we get actually is that because of the fact that it's not symplectic, it has a tendency to not conserve equipartition between different species. So actually, we do get dynamics. Dynamics is qualitatively correct, but can, diffusion coefficients can easily be off by a factor of 2. But this is not so. This is really actually connected to the errors in sampling. We have actually there is a preprint of a symplectic version of these that gets very, very good dynamics and very good sampling. And the issue is that the reason why I say that it's not ready for prime time yet is that you need an implicit integrator that makes it, brings down the saving to a factor of 2 that is less. At that point, it's a little bit less exciting, I would say. So we hope to be able to improve the implicit integrator so that that will become as fast as this.
Very interesting. I have a question. I like your philosophy of saying, okay, it's such a great speed up that I'm willing to risk. But if you want to use this approach in a predictive fashion, how do you know when you are wrong?
That's a excellent question, and that's the same reason why I would say never ever use direct force predictions alone, because it's also contrary to equivariance, which is very easy to check for, because you just every now and then you do one of these grid evaluations and you get an idea if you're doing something horrible. Checking for lack of conservative behavior is very hard because you have to evaluate the Jacobian. So an easy thing to check here is actually the drift of the conserved quantity. So the drift of the conserved quantity that you can still evaluate with some tricks is the best way that we have found this far to get an idea if you can trust the results or not. So in a way, we are back to the early days of molecular dynamics where people were obsessing over energy drift, maybe. But now you can do time steps that are 100 times longer.
Just a quick comment. Can you imagine to correct the results with hybrid Monte Carlo techniques?
If it's symplectic, yes, because you need volume conservation to be able to do hybrid Monte Carlo.
While you are not able to compute to learn also the Jacobians together with the forces.
You could learn it.
Learn.
But it wouldn't be exact. And so this far, my impression is that it's better to make it symplectic
than to learn the
Jacobian, because the Jacobian is a huge object.
You actually need just the determinant of the Jacobian to do the move, no? So you don't need all the Jacobian. No, so one can imagine to target this as an extra head.
Yes, one could put it as an additional, but during training, you still need to evaluate the Jacobian to compute the determinant of it, and that's a mess.
More questions?
Thanks, Michele. Very nice talk. Just a general question. Do you usually include the charges in your fits of the models?
Not in anything that you have seen today. We are doing this. The main issue is that there is I mean, it's just like switching on Ewald on top of an empirical force field, it gets more expensive. And in many cases, you don't need it. But yes, we are working on that. Yeah.
All right, so if there are no more questions, I think we can close here this first session. We thank Michele again for his great talk. welcome back. I think we can start. The next speaker is Laura Gagliardi, who will tell us about multi-reference method and machine learning for spectroscopy and reactivity. Please, Laura.
Good morning, everybody. It's really a pleasure to be here. I feel honored and happy. And as everybody else, I'd like to congratulate with Michele. This is a picture that was taken just a couple of months ago in Oslo. So I mean, I've not worked in my early career with Michele, but I've always admired him because he's a smart, bright, he's funny. And we both love Italy and Sicily, right? So we share this in common, our country. But today I will tell you about some of the work that we do in my group, and actually I had the pleasure of enjoying working with Michele, not early on, but recently, so I will tell you about a project that is going on now and of which I'm super excited. So I am a quantum chemist, and I've always been interested in my career in strong correlation, which for quantum chemistry, it means having many electronic configurations that should be treated in an equal footing because they are degenerate or quasi-degenerate. And in terms of applications, so we are interested, of course, I started in molecular systems, but over the years, my interests have expanded in more complex systems. Here you see a defect on a metal oxide. This is a metal organic framework where reactivity occurs, and the methods that have been developed many years ago in quantum chemistry for multi-reference systems, of course, are very expensive. So one of the goals in my research is to develop some of these multi-reference methodologies for extended, strongly correlated systems. And so the problem here is that, you know, if we think about electron correlation in a molecular world, we have a single picture description, like a single shot where you say, I put my electrons in the orbitals in one way, and this could be Hartree-Fock, so DFT in a way is a one electron theory. On the other hand, you have the complete CI, all possible electronic configuration that you can generate by occupying your orbitals in all possible way, but the problem here is that this scales exponentially or factorially with the number of electrons and orbitals. And you can think about the same situation if you study a periodic system and you have a band structure instead of molecular orbitals. So one way is to work in this middle ground in which you basically choose a so-called active space, a set of orbitals and electrons, and you allow everything to happen here. So this is less expensive than this because the exponential scaling is only within the active space. But of course, there is a lot of chemical insight that has to go into this choice. And these methods were developed in the 70s, in the 80s by Klaus Rudenberg, Björn Roos with this active space concept. So I've been working with these methods in my career, and the idea is if you have here this exponential scaling, can one reduce by thinking about smart ways? For example, you can, instead of having just one box here, you can have 3 boxes and you impose some rules. And so again, the number of configurations here is significantly less than there. Or what we have been working in my group quite recently are concepts of localizing these active spaces in really different fragments of your molecules and then write your wave function as a tensor product of these localized wave functions. And here, of course, the scaling is much more convenient than in these cases, but these are more approximate wave functions. The point is that when you have one of these qualitatively correct wave functions, to get your energetics and your properties correctly, you have to go beyond the active space. And historically, people have use perturbation theory. So you have CAS followed by PT2, or NEV-PT2 is another version of that method. And of course, these methods give reasonably good results both for ground and excited states. The problem is that when you do PT2, you know, if it works, it works. If it doesn't work, it doesn't work. And it's not that there is a systematic way to improve it. And also, if these methods scale as the second or the two-body density matrix, when you go to PT2 on top of one of these wave functions, you go to higher order density matrices. So the methods are even more expensive. So in the first part of my talk, I want to describe a method that we have been developing, and this is work that I started when I was in Minnesota in collaboration with Don Truller. So this is a way to try to merge the best of the wave function world and the density functional world. It's a new form of density functional theory that we called multi-configuration pair density functional theory. And the idea is to start from one of those wave functions, the CAS, GAS, and so on, and then basically compute the total energy in one shot with this expression, in which basically this is the classic Coulomb interaction. This is the nuclear-nuclear repulsion energy. So we can think that these three terms are what we call classical energy. And then there is this energy functional. This is we call it on-top energy functional. It's a non-classical functional that basically is a functional of the one electron density and the on-top density. The on-top density is the trace of the two-body density matrix. And so it has some of these multi-configurational character. So in a way, there is an analogy with Consham DFT. The difference is that rho and pi come from this multi-reference, multi-configurational wave function. And so the question is, how do we get to the functional? So if we have our energy classical plus non-classical, what we have been doing is just borrow some functional expressions from Consham DFT and translate them. So the idea is to use a relation between the spin density, the total density, and the on-top pair density, expressed through this capital R that depends on the on-top pair density. And so one gets these pi and rho from the multi-reference calculations and use this relation to get some effective spin densities that can be used in the functional form. And so in analogy to what one does in Consham DFT. And so we have a local version of this method, which is just a translation of PBE. So translated PBE, a hybrid version, TPBE0, in analogy with PBE0. Actually, more recently, we have also a meta GGA expression. So the advantage of this method is that you pay the cost of the initial multi-reference calculation, but then the energy comes for free, so you don't have to do perturbation theory on top of that. And in principle, this method describes a multi-reference system. So this is an example. I want to show you, it's a benchmark of excitation energies of organic systems. So the point about these methods is that they can treat really in an equal footing ground state and excited states. Unlike in Consham DFT, where, you know, when you start studying excited states, there can be some challenges. And so here you can see these are different active spaces, different basis sets, different number of data, and you see the mean absolute error. So we can think that NEV-PT2 is a sort of reference, a standard in the field. The parent wave function alone does not do very well, but when you do this wave function with these functionals, the results are of similar quality to NEV-PT2, and as I said, they are significantly cheaper, and also you don't have all the problems of intruder states that you have with perturbation theory. So computing vertical excitations is relatively straightforward in this work because, let's say, you choose an active space, and ideally the active space is the same for your ground state and your excited state. But what about if we want to study reactivity? I mean, studying reactivity with these methods has always been quite tricky. And the problem is the following. I mean, we like to use multi-reference methods when these methods do not capture the multi-reference character of the problem, and we want to describe, the reason is that we think we can describe in an equal way a reactant, products, and transition state. But historically, what people have done is to say, well, how do I choose my active space? I think about the orbitals that are involved in bond breaking, bond forming, and I try to choose an active space consistent along my reaction. However, there are a lot of challenges with that. One is to use chemical intuition. It's difficult to apply this approach in a high throughput fashion. And also, if the system increases, how do I make sure that my active space is still affordable? And for this reason, I can tell you, I mean, these methods are a sort of niche area. If you look at how many data are there generated by DFT versus this, we are talking about different orders of magnitudes because these are not black box calculation. So ideally what we have been trying to do, and this is work started by Daniel King, who is now a postdoc, and Jacob, who is a student, is really to develop a high throughput approach that allows us to choose active spaces in an automated way, and that is also cost effective. And so the method that Daniel proposed is called approximate pair coefficient. And so the idea here is that a user has to still, at the moment, select a maximum number of orbitals and electrons, but just the number, not which orbitals. And then the orbitals are ranked based on the orbital entropy of the occupied and virtual orbitals from a Hartree-Fock calculation. So the user has just to perform a Hartree-Fock calculation, and the orbital entropy is related to the one-body density matrix, which can, if you have the Fock calculation, you can really obtain directly from this coefficient that is computed using the Fock and exchange operators from a Hartree-Fock density matrix. So in principle, once you do your Hartree-Fock calculation, you can already compute this orbital entropy, and then you decide, you apply a sort of threshold, and you say, we remove from your active space all the orbitals which have an entropy lower than this threshold, and in order to contain the number of configurations in your wave function. And so the higher is the orbital entropy, the more the orbitals are entangled, and so the more they contribute to this multi-reference wave function. And then with such a prescription, one has a final active space. And so here, Jacob and Daniel use this approach. I will show some results about a large data set of organic reactions. And so the idea here is if you have your reactant, your product, your transition state, you'd like with this automated active space selection to reproduce the hand-selected results. So you want green to be on top of black, and when the system is multi-reference, you want to see the difference compared to the single reference calculations. So here, basically, one is to select geometries along a reaction coordinate, apply this procedure, so this scheme to a Hartree-Fock wave function at each geometry, perform KSSF calculation with this active space, and then compute the post-KSSF energy with this pair density functional theory. And so the first application has been this set of organic reactions. These are computer-generated organic reactions. It's this database with about 900 reactions with only species containing carbon, nitrogen, oxygen, and hydrogens. And we have been looking at reactant products and transition states. And so this APC with this maximum active space is our automated approach, and we have used it just to generate the parent wave function, but also to do this post-CAS treatment. And then we have some single reference results with R3-FOC PBE, which is also what is called density-corrected DFT, and MP2 or couple cluster single reference limit. Also, we want to have a way to evaluate the degree of multi-reference characters, because it's not always needed, okay? And so this is a kind of descriptor, the M-diagnostic, which basically tells you the degree of multi-reference characters based on the occupations of the doubly occupied, LUMO, and the single occupied orbitals. And so based on the value of M, one knows if one is dealing with systems that are more multi-reference or less multi-reference, and whether these treatments are needed or not. And so I want to show you an example of one of these reactivity studies. So again, these are computer-generated reactions, so the physical meaning can be disputable. But here you say we have a reactant, product, and transition state. And in this case, the product is quite multi-reference, this large diagnostic. And you can see here we have R3-FOC PBE, we have B3-LIP D3, CCSD, parenthesis T. These are all single reference methods. And here we see the multi-reference treatment. And you can see there is a disagreement between the single reference and multi-reference treatment. Some of the single reference really predict that the product is higher than the transition state. So I think this is important also for a community that uses Concham DFT as a tool, as a high level, to keep in mind that there are these situations. And you can see here what is important. These are the orbitals of the product, and you see there are these two orbitals with occupancy of about 1, even if this is a singlet state. So this is an open shell singlet. It's a diradical system. And this feature is captured by this approach, and sometimes these situations are very challenging in Concham DFT. But to show you the distribution of these reactions, here we are stratifying them based on this M diagnostic. And you can see, so this is low multi-reference character, high multi-reference character in between. And this is the energy difference between reactants and products. And here, these are the activation energy, so reactant transition states. And this is the stratifications, the difference, deviation from the single reference limit. So we see that in general, when we have low multi-reference character, the single reference and multi-reference agree pretty well. And so we say that this PDFT shows a smaller active space inconsistency error than NavPT2, and so it's also a further advantage compared to this approach. But then when we go to multi-reference situations, we see that there is a big discrepancy between the single reference and multi-reference, which means that, one has to treat these situations very carefully when doing Concham DFT. So this was our first big data exercise with these methods. And of course, now we want to study not just these automated reactions, but also catalysis. And for example, this is the methane abstraction catalytic methane hydrogen abstraction, which is catalyzed by a metal oxide, which is a node of a MOFs. And we know that catalysis involves complex electronic structures. In these cases, choosing an active space becomes even more complicated than before, because you want to really localize your treatment in the region of interest, and because you started having d orbitals, not just P and S. So we are working in this direction. But again, once again, I want to show you for this step, just going from the pre-complex to the transition state, you see these are the different energy values that you can obtain by using different methodologies. And you see the first four, so green and blue on these pictures are Consham DFT, local or hybrid, and meta GGA. And you see, on the other hand, the multi-reference results are up here. So in general, we can say that there is a difference of about 100 kilojoule between multi-reference and single reference, which again will affect the way in which you train your machine-learned force field when you use these Consham functionals. And on the other hand, these semi-automated active space approach, they really have, for example, the CH bond consistently between reaction and transition state. So the selection approach of the orbitals is consistent, but also, I mean, this energy difference is important to keep in mind. So we can compute energies, we can compute gradients analytically with this approach. So the question is, can it be used also for excited state dynamics? And to summarize, the pros of MCPDFT is that is in general as accurate as CASPT2, but it scales as the parent wave function. However, the cons are that the initial formulation is that it is a single state method. It does not account for state interaction. And so when you want to study, for example, excited states, or you have situations where there is a strong nuclear electron coupling near conical intersections or avoided crossing, the method MCPDFT becomes inaccurate. Here you see this is a classic example, the lithium fluoride dissociation. So what we have done is to develop, and this is work led by Matthew Hennefart, who graduated last spring in my group. He has developed a state interaction version of the methods. It's called linearized pair density functional theory, which really describes the topology around conical intersections properly. And so it's now possible to perform also these excited state dynamics. Here, for example, you see the trajectory for the CN bond dissociation. And here there are some details about how these simulations are performed and the software that we are using. So this is the all traditional quantum chemistry development that we have been doing. And now the fun part starts, and this is the collaboration with Michele. And so, how much time do I have? 3 minutes? Okay, I will be fast. So what, there was this paper, only 3 minutes, are you sure? I think you are, okay. I didn't start at 20, okay? I started much later, but okay, maybe I will finish it in 5.
You can tell your story.
No, I will be fast. So this is the paper that Michele wrote a few years ago, very interesting study in catalysis. And then there was this comment by Veronique van Spreebock. So they basically trained the machine-learned potential on DFT, and this works for the type of systems they studied, but what if we have this partially D and F shell? And so I reached out to Michele and I said, why don't we try to use our multi-reference methods to train the machine learned? And we decided to look at this model reaction. It's a simple, it's small, but it's a typical case in which you see the transition state captured by Consham is significantly off compared to this. And we know that this is right because this gives the right rate constant. So in collaboration with Michele's people, we started working with their collective training data approach. And the beauty is that I don't have to talk about it because Umberto and Luigi are following up after me, so they will tell you everything about it. But so this is what they usually do when they perform this Consham training. Now the problem is that when we want to use a pair density functional theory, our method does not just depend on the geometry, but also on the multi-reference wave function. So there is this extra degree of difficulty in the active learning cycle. And so this has been an extremely humbling and learning experience for us, because doing this step, I mean, initially we didn't know how to do it. At some point we thought the project would go nowhere. But then Aniruddha has come up with this suggestion. So the idea, this is an interpolation scheme. So let's say that you have your geometry and molecular orbital coefficients for 2 points in space. You want to have them at this geometry G. And the idea here is really to interpolate between these two using a weighting factor that can be obtained as the inverse of the distance between the two geometry. And then one can has a new set of molecular orbitals orthonormalizes them. We call this method the WASP active space protocol. And so the idea here is that if we have these sets of steps, instead of having to do a guess calculation at every geometry, ensuring consistency, with only a subset of geometries using this interpolation scheme, it was possible, so in this case, just these four, to reproduce exactly the same potential energy curve. And so it's smooth and it requires fewer calculations. And the same could be done along a trajectory. And so now, in a way, we know how to do this. Simone and Umberto and Luigi will talk about the efficient sampling with DEAL, so I don't have to talk about it, but this makes the calculation much faster. And so we were able to perform this PDFT accurate catalytic reaction dynamics with the machine-learned force field. And here, basically, you see that there are a lot of trajectories which are very spreaded. The transition state is not just one, but there is an ensemble of transition state. And so this is our dynamics, which I don't think I can run this, but it's not a problem. But the point that I want to make is that we were able to perform these calculations. So this is what the traditional MCPDFT calculation would take. This is what our WASP MLP calculation take, but we got this MCPDFT accuracy. And so these times are competitive with what one can do nowadays with DFT maze, okay? So we are in business with DFT, but with a significantly higher accuracy. So in the future, now we are working again with the Parrinello group to extend this approach to excited state dynamics using also embedding approaches. With that, I'd like to thank you very much, Michele, Umberto, Luigi, and Simone, and all of you for your attention. And if you have questions, I'm here.
Thanks very much. Questions?
Thank you, Laura. I think it's very, very important to have these high accuracy methods, because otherwise we are training machine learning models on garbage. So it's really, really good. So my question is, how can we hope to get these kind of accurate quantum chemistry also for condensed phases, transition metal oxides, actinides, and whatnot.
So we are now looking at variants of the methods also for periodic systems with periodic boundary conditions. It's an area of development, and we are not just the only ones. Again, they are not as black box as we would like to be. So, but I think it's a very interesting area of research. Yes.
Okay, thank you very much. I am Amaru from Ethiopia. I'm happy to be here in the ocean of scientists, and I have only one question for you. Is it also possible to study with the methods you reported heterogeneous catalysis that involves multi-product system, like if I like to crack long-chain hydrocarbon, that will give me range of small number, different range of products. So is it possible to study the selectivity of maybe a zeolite catalyst?
I mean, I showed you an example of a MOF node which has similarity with the zeolites. Of course, I think the problem in catalysis is your model has to be realistic. So, and also, you know, at the end what we get are free energies, if you're lucky, or electronic energies. Catalysis is not just about electronic energy. So maybe you have to get selectivity right, you have to build microkinetic models. So it's a much more complicated, but it's good if you have reliable electronic energies. Okay.
Maybe if I don't see other questions, maybe I have one. In this weighted sum, you use 1 over the distance. Mm-hmm. Why not another function like the exponential of minus the distance, or 1 over the distance square, or the distance cube?
These are all possibilities that could also be explored. Yes, it's not the only one.
So you just tried 1 over the distance?
We tried because otherwise at the beginning we thought we wouldn't be able to do it.
But maybe the physics of level crossing, cannot the physics of level crossing guide you in the choice of this weighting, the functional form of the weighting factor?
That could also be a possibility, yes.
All right. Thanks very much. Okay, so if there are no further questions, we thank again the speaker, and we move to inductive learning for interatomic potentials.
Grazie mille. Okay, so thank you very much, and it's really a great. Never mind. It's really a great pleasure to be here, and sorry, sec. So before diving into the topic, since when I started my PhD with Michele, I've been working in integrating machine learning and unsampling techniques from the data-driven discovery of collective variables to the construction of machine learning potentials for rare events, and more recently, been very nice to follow also Michele's enthusiasm into the field of heterogeneous catalysis. And here I was wondering what to present. In the end, I wanted to present some recent methodological works on the field of constructive machine learning potentials, which we have already heard this morning, also from Michele. It's really a hot topic nowadays. And this, of course, started. I mean, at least the application of the first application of high-dimensional neural network potential goes back to the pioneering work of Beller and Michele almost 20 years ago. And we could say, in general, still, I mean, we could say that the steps needed to construct such potentials are: first, we need to construct a reference database.
We need to choose how to represent the environment, the configurations, and then finally we can do the actual fitting. And in the course of this talk, I'll try to show how we can address all of these three different ingredients. And of course, one interesting thing is that the construction of the training set, especially for reactive events such as phase transitions or chemical reactions, is still a non-trivial challenge. Because of course, as in a similar way as also Pratish was saying this morning, is always a chicken and egg problem. So you don't know beforehand which are going to be the relevant structures. And of course, what comes to our help is our enhanced sampling methods. And which is exactly, although they've been designed to accelerate the rare events and escape in the local minima, this is exactly what we need also to train robust and reliable machine learning potentials. And indeed, if we look at them from the perspective of the probability distribution, we see that their effect is typically the one of sampling a much broader distribution, which do not cover only reactant and product states, but especially the high free energy configurations, such as transition states. And the combination of machine learning potential and unsampling are really been really successful in describing a lot of systems and physics and chemistry with an initial-like accuracy, but at a tiny fraction of the cost. Here, and you see, it's a really a kind of broad and general thing. So this is a movie from the first paper I did with Michele on studying silicon crystal nucleation. And you could do microsecond-long simulations for thousands atom systems, and you can really see with an accuracy close to the DFT one how the nucleation process behaves. And then we did phase diagrams, phase change materials, then chemical reactions in water, and more recently also we've been focused on heterogeneous catalysis. So it's really a broad and general tool. But of course, the point is, it doesn't come for free. And the number of DFT calculations that were powering these studies were quite significant. Just to give you some numbers, when we started looking at a single nitrogen molecule breaking on a bare metal surface, we take about 30,000, 25,000 DFT single point calculations. And then we started including more steps, then we went more than 100,000, and then when we were adding more configuration, this number was really skyrocketing. And of course, if you like to go beyond and to increase the level of complexity, but also accuracy, I guess you cannot run 500,000 of single point with Laura's methods. So this of course precludes the routine usage of these methodologies, but also to scale up to more complex systems at a higher level of theory. And for this reason, this motivated for a quest towards data efficiency. And so we ask, how can we efficiently learn machine learning potentials for cases in which we have few and no costly reference data? Of course, many of the works that I showed before were run with DeepMD, which is not that efficient. But which are the ingredients? Of course, on one end, we need data-efficient architectures. And by this, I mean architectures which are able to produce a stable and accurate MD with just a few quantum mechanical reference calculations. And I show an example about using also transfer learning to achieve this. But of course, we also need to know which are the few relevant structures that we should use to train our machine learning potential. Because of course, once we have a big data set of every configuration, then we can always subsample it. But we need to find it on the fly. We don't know beforehand which are the relevant structure, especially the reactive ones. And so we need a more data efficient active learning scheme. And so I will start from the second aspect, which is data efficient active learning for training machine learning potential, especially for here applied to chemical catalytic reactions, but it's of course much general. So here the objective that we wanted to pursue is how can we obtain a uniformly accurate machine learning potentials. Of course, we know that it's crucial to have a uniformly good description. For instance, reaction rate depends exponentially on transition state energy. So if we have a small error there, we will get order of magnitude errors in rates. And on the other hand, we also know that machine learning potential, at least they do not extrapolate too well. their training set. In the sense that, for instance, here is an example of a potential train on your reactant and product. You see that although the aggregated error, like the mean absolute error, is just a few tenths of millielectron volt per angstrom, the uncertainty, the error in the middle, it can go as high as 1 electron volt. And so this, of course, we would like to transform this into a uniformly accurate description with as few calculations as possible. And so we ask, what are the ingredients? So on one end, we need to sample, so to discover and to sample what are the available reactive pathways. And especially at the beginning, we would like to be very incremental, because we don't want to take the wrong direction and then starting adding configurations which are maybe are not the minimum free energy paths, right? And on the other end, we would like to need to just select only the few relevant structure out of those. And so, together with Simone, he also has a poster, we came up with a two-stage scenario, two-stage workflow. In the first part, we wanted to discover which are the available pathways. And so we combined two different things. On one end, we use Gaussian process regression, which is a machine learning method which do not only produce a prediction, but also a confidence. And so we can use it to what has been called uncertainty-aware molecular dynamics. So typically, you know if you can trust the model, and if you don't, you perform a single point calculation, and you add it immediately in an online fashion. This is the difference with respect to maybe other methodologies. And we combine this with an unsampling, particularly we use OPES, and we use it in the flooding variant, in which we just fill the reactant basin, and then we let the reaction to occur as spontaneously as possible out of the basin, in order to not affect too much, for instance, with the choice of the collective variable and so on. But of course, also, in this case, we didn't want to add much information. And just to give you an example of how it works, so in this case, by combining, we can do what we could call uncertain-aware and unsampling, which the unsampling is bringing our system out of the reactant basin, and then as soon as it encounters some structure which is dissimilar from the one already contained in the training set, it performs a DFT calculation. We optimize it on the fly, and so by doing this, we can collect an initial dataset of reactive configurations, which are the points here, which is exactly, which you can see are exactly in kind of the transition state regions. And the accuracy went down quite a bit, but still we are far from the uniform. So the question is, after we discover which are the possible reaction pathways, we would like to then converge them to a uniform accuracy. And so we can use the usual active learning, which we train a first potential, like we use MACE, which of course is being an equivalent graph neural network, is much more data efficient. And so we can use it, the active learning. But the question always is, how do we, when we then use it with the active learning scheme, it means that we use it to generate new structures using an unsampling, and then we need to identify a few of them to be recalculated at the DFT level. But of course, we have millions of configurations from the molecular dynamics simulation. So the question is, how do we select only a few relevant structures? And the typical strategy is to use what's called query by committee. So we train an ensemble of models, and we use the standard deviation of the predictions to detect where are the uncertain configurations. And here you see an example, an histogram of the selected configuration along some collective variable. But then the problem of this methodology is that it produces a lot of redundant structures, because maybe in the same simulation we have observed, with the same level of theory, we observed a lot of similarly maybe wrong configurations, and we don't want to add all of them. So what we did here, what we call a data efficient active learning, has been to, again, connecting us to the first part, to use again Gaussian processes to select only a minimal data set of non-redundant structures. And the key point here is that we do it in an online way. So we go through all of our configuration, high uncertainty configurations, and then we ask, do we still need to add them do we still need to add them after we already selected one for DFT labeling? And this actually can be done in a completely parallel way. So we just select them using a Gaussian process, and then in parallel, we train them. And by doing so, just a matter of adding, for instance, in this case, a few another extra 100 configuration, we see that we were able to obtain a uniformly accurate description. This was the nitrogen breaking on a metallic surface. And so with this workflow, in a matter of less than 1,000 single point calculations, we were able to obtain a uniformly accurate potential. And this actually was even before the universal potential, so it's a lot of configuration were actually from the initial reactant and product states. And why is this important? Because I would say it really allows, as Laura was saying before, to go into two different directions. On one end, to go towards more complex systems than what we were able to do before, and also higher level of theory, as she just showed an example in PDFT calculations. And just to give you here instead an example of the other thing that we were able to do, so more realistic modeling, I'll just show an example of a work that we're doing in collaboration with experimental colleagues, in which we wanted to understand the origin of the promotional effects of alloying on some catalytic reaction. And there was an experimental evidence, but there was a clear understanding from the microscopic point of view of what was the origin. And of course, what we wanted to do is to model this reaction in a more, all of the key steps of the reaction in a more realistic way. And this, of course, for instance, includes explicitly encoding also lateral interaction with other adsorbate and intermediate species. But why this is a problem? Because if we think from the point of view of the different environments that we have a huge number of environments that we should be able to simultaneously describe. And instead, what we did, we started from these configurations, and then with using this data efficient active learning scheme, in a matter of just a few iterations and a few thousands of DFT calculations, we were able, again, to describe across a wide range of different environments in terms of interactions with adsorbates and intermediate species, the key reactions. And without entering too much of the details, so this allows us to really understand, for instance, the difference between iron with respect to the iron-cobalt alloy in terms of the competition between atomistic processes. And this has been really nice to validate this with experimentally in terms of this competition between different atomic processes, which have been really enabled by a more realistic modeling of these systems. And if you're interested, you can check out this recent preprint on ChemArchive. And here I would like to briefly discuss I would like to briefly discuss the other part, which is about transfer learning. So we asked, and this is about the other part of the other ingredient about data efficiency, which is, can we do even better in terms of machine learning architectures, after having used a few of them, and to introduce these, I'd like to start from what are the traditional ways of building machine learning potentials. So starting from like Beller Parrinello symmetry functions or Gaussian approximation potential, one family, especially at the beginning, used to build them starting from some physical descriptors and then building machine learning potentials like using neural networks or kernel. So here, we at the beginning, we were used to choose these representations. But then, of course, this requires a lot of hyperparameters of the descriptors and so on. And then more recently, as it's been already mentioned quite a lot, the message passing graph neural network have emerged as a promising alternative in which we could say that the physical descriptors are learned in a data-driven way using the message passing step. And again, as Michele was saying, we observe a lot of large data sets, Meta arrived to almost alpha billion of configurations, and together with them, there have been a lot of effort of creating general purpose potentials, which are based on such architectures. And the question is, okay, of course, on one can and should try to fine-tune them to the specific application of interest. But the question is, can we frame it in a more broad way in terms of transferring the knowledge? How can we effectively leverage the knowledge that these models have learned such that we can adapt them in a more in an efficient and also simple way? So this goes into the broad transfer learning. This has been a collaboration with the machine learning group at IIT. And so what we came up with was a transfer learning which combines actually the best of the two worlds, of graph neural network to learn a representation and of traditional kernel-based models, actually large-scale kernel models. And how does it work? Essentially, we assume that we have a graph neural network trained on possibly a large data set of configurations. And then the first ingredient is that we extract a representation from the graph neural network. So we extract the invariant descriptors as, for instance, the node features of a GNN. And then what we do is that we transform them using a large-scale kernel technique, which is called random Fourier feature, which allow us to approximate a kernel function using, by transforming them into some nonlinear space in which the kernel is expressed just as a scalar product. And this eliminates all of the poor scaling of kernel methods, for instance, in terms of the number of samples. And importantly, this can be implemented just as a linear, just as a single layer neural network where the parameters do not need to be learned, but just the sampled ones. So this is extremely efficient. And the other advantage of this method is that it inherits all of the favorable properties of kernels, such as the fact that we have a convex loss function, which we do not need to optimize with gradient descent, but we can just optimize in a single shot in an exact way. And the consequence of this is that we can reduce the training by order of magnitude compared to both kernel based on physical descriptors as well as traditional graph neural net. Here we take the TM23 dataset and we evaluated the speed and also the accuracy across all of the 27 elements they consider. And what was interesting to observe is that we obtain a much so we can optimize it in a single shot, but at the same time we get something that is as good as the best kernel optimized on per each element. But here he said we don't have to choose anything. And then what we can use this for? Well, for instance, it allows for a very simple way of fine-tuning pre-trained machine learning potential, for instance, to different level of theory. We know, and it's already, Pablo already told this morning, water is very sensitive to the details of the electronic structure. So, for instance, Mason P0 is trained on PBA, is known to produce an overstructured water. So, how can we correct this? And so, we were in this example, so we have the zero-shot prediction, which is, and then we were taking a kernel reference of a small but highly curated data set of DFT calculations. And here you can see how we've already, with a few samples, we were able to be to obtain an accuracy as good as the one of the kernel based on physical descriptors trained on the whole data set. And of course, it's not important. It's not enough to just look at energy and force error, but it's always important to look at the error that we do when we then perform the actual MD simulation. So we checked different structure and dynamical properties, and again you can see here with as few as like 8 samples in this case, we were able to obtain an almost indistinguishable result from the data set. And then we also have some other more complex examples like interface between water and metal surfaces in the paper. But then, as a last example, I would like just to show some ongoing work in which we were saying, okay, this data efficiency allow us, for instance, to
quickly check different level of DFT functionals. For instance, here together with Pedro and Umberto, what we did, we wanted to check proton transfer reaction using different functionals, and then what we did here was, okay, we start from a pre-trained potential. We use MESOF, which was trained for organic molecules, and then we use it and we collect just we use it to perform the reactive simulation. We select just a few samples, and in this way, for instance, we were able, with as few as 50 DFT calculations, to check the free energy in a very accurate way, the free energy barrier for this proton transfer reaction for different different DFT functionals, but of course it could be beyond DFT methodologies, because if we just need a few tens of samples, even if they're very, very expensive, we can now afford them. And so I think this just to summarize this second part, this transfer learning approach can be seen in different ways. So we can look at it as a kind of large-scale kernel technique, in which this descriptor are learned from in a data-driven way from a message-passing neural network, but we don't need to tune the hyperparameters, and it also avoid the poor scaling, and it can also be seen as a principal way of fine-tuning universal potentials with fast and exact optimization. So, because in the end, what we are doing is just replacing, for instance, the head of the graph neural network with one based on random features. So for this reason, we call it fast and Fourier features. And if there is the preprint, has been accepted on MPJ computational materials. And also, if you want to try it out, the code, everything is ready to use. We support Maze, 7net, and a couple of backbones. And you can immediately use it. There is a Colab notebook, so feel free to try it out and give a feedback. So I would say in this talk, to summarize, in order to scale machine learning potentials to more complex, to simulate, for instance, reactive, so challenging events like in heterogeneous catalysis, we really need to address these two ingredients, which is going towards more complex systems and also a more accurate level of theory. And the combination of these approaches hopefully can go in this direction. And before the last thing, we just, so this is a different topic, but we just uploaded a review about the integration of machine learning and unsampling to archive, which I did together with Enrico, which is here, and also the collaborators. And here we wanted to, we covered the developments, both in terms of developments from data-driven discovery of collective variables to more recent biasing schemes and generative modeling, also as Pratius was mentioning this morning. And but also we wanted also to give a thorough perspective of the different applications that these methods have enabled. And it has been really, and many of these methods and applications have been made possible by the work that Michele, together with the group, had done in the past few years. So it's been really nice to see the impact in a very broad, terms of methods, but also applications. So going from catalysis to biology to chemistry and physics and so on. So if you have feedback, it will be very appreciated. And with this, I'd like just to thanks the people who've been involved in the work I showed, which are mostly Simone for the data efficient active learning, Pietro and Pedro for Frank and this transfer learning approach, Enrico for it also has a poster about this machine learning library for rare events, and of course all of these will not be possible without everything. I mean, I really think that these methods have been really based on what I've learned from Michele, both in terms of doing science, and so I would like just to say thank you, not only for the excellent science, but also for creating such a nice environment. Here are a few pictures of the Parrinello's barbecues and groups over the past few years, and with this I say thank you for
Thanks very much. Very interesting. Questions?
Thanks, Luigi, for the very, very nice overview. So I have a quick question about that example you presented on water and using the MACE foundation model and how to fix it, so to say. So I was wondering how much it suffers from the previous knowledge, so to say, how difficult it is to make the potential forget its own initial training and to make the fine-tuning, so to say, more important.
So thanks for the question. So I would say we are not just fine-tuning, but we are kind of decoupling the representation learning from the actual fitting of the potential energy surface. So in this scheme, what we are doing is that we are kind of just extracting not what it has learned in terms of structure energy relationship, for instance, but just a way of representing the local environment. And so this is the representation learning part, and then we are the part, the structure property relationship, we would say, is left to this kernel-based technique. So I would say that it's not much about forgetting, because it's more about of course, we need a good representation. I mean, we need a good model trained on a lot of data such that it can describe in a faithful way the different environments. But I would say it's kind of different. Does it answer? More or less. Okay.
How transferable is what you learn from one system to the other? I mean, do you have to start it all over every time?
So, I would say, so these systems are always kind of specialized. But of course, the idea that you can use this transfer learning setting really goes into this direction, because you can really reuse the information that you have already learned to reduce the number of configurations that you need. And so if you can do this from a pre-trained model to let's say a specialized system, you can also do the same trick using a pre-trained potential is trained on a given system and then apply it to a slightly similar. So I would say that this is again, it's not zero shot, which means that you don't take it and use it as it is, but it's a few shot learning. So it allows just a few additional points to be transferred to similar level of systems. Yeah.
I don't see more questions, so I think I have one once again. Okay. I'm sorry. So in the typical paradigm of transfer learning, a critical role is played by depth, in the sense that you have a deep network, and then you typically transfer, let's say you have 20 layers, and then you transfer the first 15. Mm-hmm. While in your case, you are going in a direction which is random feature models with a very, very wide. Yeah. I'm a little bit puzzled, because typically the standard paradigm is that depth is essential to do an efficient transfer learning, while you are doing in a shallow direction.
Well, we are still going in terms of depth. I mean, so what we're doing, for instance, if you have, let's say, a 5 or a 10 message updates in the GNN, okay, we need to decide at which point to stop. So, for instance, the example I showed there was MACE, which typically use 2, so we use both. But with other architectures, we tested. We actually. So this is kind of you need to choose where to stop. So of course it's a trade-off between again the quality of the representation and its cost.
But finally you are training only the final regressor. That's the thing.
Yes, absolutely. Then okay. Again, for instance, what we try to do, for instance, in the case of MACE, which has a readout, so that also depends on the kind of how to extract the descriptors. Mm-hmm. Because, for instance, some graph neural network typically update the node feature and then just use the last as the to pass through the readout to learn. MACE uses another scheme in which it takes all of the contribution from different message passing, and so we mimic that as well. So we extracted the configuration. So this is also about how to extract the representation from in an effective way. But yeah.
All right. So if there are no more questions, we thank the speakers again for this great first session.
system. In particular, like which is well known, but the problem is that this kind of process is highly energy intensive. So a large amount of energy is consumed for this particular process, and also a huge amount of CO2 is produced every year. So many studies have just been focused on proposing new architecture, new catalytic material to do this job and to do so ammonia synthesis. And from this point of view, many of these metals are basically a transition metal-free compound. So it means that we don't have classical transition metal, but we have alkaline earth metals. So basically, one of the first questions, how is it possible that lithium hydride, lithium imide, how is possible they can be catalysts? As a chemist, I will never expect this kind of compound can actually work. So, but there are many evidence, for example, that barium hydride, if you put that in a chemical looping process, is able to catalyze ammonia synthesis. What does it mean, a chemical looping process? It means that we first expose barium hydride to nitrogen flow, and then we convert our barium hydride compound in something else. And this something else is then hydrogenated, so is exposed to hydrogen, and with this kind of chemical loop, we can get a very high yield of ammonia. But now we have to say, what is our catalyst? Our catalyst is this very simple, let's say, compound, which is just has barium and has some hydrogen. So let's see how our dynamical picture allows us to describe this catalytic process. And let's see if dynamics is actually important or not. So first of all, we can see that the catalytic activity, if we go at 550 Kelvin, is very small. But instead, it starts growing up if we go at 700 Kelvin. Let's say what is the dynamics of the surface at 550 Kelvin. If we see the dynamics, you can see that the hydrogen, we tagged in red the nitrogen, is basically vibrating around this equilibrium position. It's doing nothing, much or less. If we go at 700 Kelvin instead, we can see that this hydride starts hopping inside the crystal structure. So its mobility is highly enhanced if we go at the operando temperature. But what is the result of this fluctuation? As a consequence of this fluctuation, we can see with a very small barrier, two hydride can react together and basically can lead to the formation of a nitrogen molecule, and the electron involved in this process are just released on the surface. So this means that during this process we have an activation of the catalyst. The catalyst itself is not barium hydride, but is an electride, which is formed because of the release of the hydrogen. So basically, this compound now is the actual catalyst, and we formed this catalyst by just heating up our compound. But now, of course, we have this electride and we are exposing it to nitrogen. So what is the results of this? Is that nitrogen can react with this loosely bound electron and starting being reducing. And basically, like reduction after reduction, what we can get is that nitrogen, we can weaken the nitrogen-nitrogen bond, and at the end, we will form this NH2 moiety, which are called imide. So basically, if we expose our barium hydride to more and more nitrogen, we will see that basically we are forming something which is a mixed compound. We are formed a compound which is not anymore barium hydride, but which is a mixture of hydride and imide. And if you see this particular compound, if we see the dynamics of this compound, we can see that the mobility of all the atom now is very, very large. So we can see both imide jumping in different octaedrical sites. We can see hydride moving everywhere inside the crystal. But what is most important is that in this first step of our chemical looping process, we had something like a phase transition. We first converted our electride in something which is a mixture between hydride and imide. And this mixed compound has very important properties in terms of mobility of hydride and imide. Then as a second step of the chemical looping process, we say the experimentalists, they turn off the nitrogen flow and they open the hydrogen one. And you can see that in this case, for example, if you have your compound and you expose it to hydrogen, basically what we see is that first the amide are hydrogenated, so you start forming basically amide, and then at the end, like this amide can also be hydrogenated and you release basically ammonia. So we can see that also in this case, the high mobility and the dynamics of the catalyst is very important. But what is most important is that basically we start our catalyst is not the compound that we have put it inside, that we have loaded inside the reactor. We started by barium hydride. We first activate the catalyst by heating up and bringing to the operando condition. Then we expose it to nitrogen. The electride react with nitrogen and we form this mixed compound, and then at the end, again, the mixed compound is hydrogenated and we form back our original catalyst. Of course, so this is, let's say, part of the story, because if we want to get, if we want to realize this ammonia economy, then we also need to be able to decompose ammonia. So in the first step, we saw how we can use different catalysts to synthesize ammonia. Now we want to see how we can decompose it. And one of the compounds that we start studying is this lithium imide compound. This is also particular, exotic, let's say, compound because it's a ionic compound. The first question you ask yourself is where I'm going to put the electron in all this redox process when I want to synthesize or reduce ammonia. But if we see, from an experimental point of view, there are many evidence that lithium imide can catalyze this reaction, and if you put some ruthenium, it can also, the yield of the reaction can also be very large. So also in this case, the question is how this works. So we started this kind of work with Professor Mei Yang, now professor at Nanjing University, where we started looking at the dynamics of this lithium imide compound. And you can see that if you start the pristine material, so we started with lithium imide, the dynamics of this compound is what we will expect. So you can see that that is a surface, the 111 surface, and you have basically that this nitrogen atom, we are reporting a scatter plot of the atomic position. You can see that they are just oscillating around their equilibrium position, and that's it. So much or less, this is the standard dynamics of an ionic compound. But what happens when we expose this compound to ammonia? What is happening is that you have a series of proton transfer reaction, and you can see that the dynamics of the interfacial layer now is completely different. We have an almost liquid-like layer that is formed at the interface, and this is actually what is our catalyst. So the reactions are happening in this very highly fluctuating environment, which is formed at the interface, in which we have the formation that catalytic, let's say, active configuration can be easily formed and destroyed depending by the fluctuation of the surface. And in this way, we can get many reactions that lead to the decomposition of ammonia. With Mani, now we started looking at why, when we put ruthenium on top, the dynamics of the catalyst is enhanced. So if we want to take, let's say, the classical approach in computational catalysis, we will just optimize the structure. And so we will say, okay, this is our surface, 0 Kelvin, we put the cluster on top, we are happy, and we start studying the reaction. But actually, how is true this picture for this system? How, let's say, bad is this kind of model if we want to study the catalytic process in operando condition? So this one is just a movie of the dynamics of this cluster if we go at very small temperature, so we are 300 Kelvin, and you can see that the cluster is just stay on top of the surface, nothing is happening. But let's see what happens if we go at the operando temperature, so 750 Kelvin. In that case, we can see if we look at the dynamics, we start from the optimized structure, and you can see that the cluster and the dynamics of the surface is completely different from the one at a very small temperature. You can see that the the cluster now, because of some proton transfer reaction, can also be englobated inside the surface itself. And you form this kind of highly solvated ruthenium cluster inside the surface, and this is actually what is the catalyst that we have now inside the pot. And also in this case, of course, like in this environment, you can have many possible chemical reactions with which you can have nitrogen-nitrogen coupling, hydride formation, and then at the end, you can get the final nitrogen and hydrogen. So now the question is that from all these examples, we have learned some lesson. So heterogeneous catalyst is something which is highly non-local, so contrary to what we study on chemical textbook, and also the active phase is formed in operando condition. And but now, our first step, it has been understanding the operando dynamics. So we started by using all the tools that have been developed in our field in the last few years. But now what we want to do is doing a step forward. We want to try to go to the lab. So basically, from our prediction, we want to try to design novel catalytic system. So what, for example, we did, first of all, to propose maybe some new compound, we learned that the dynamics of our system is very important. The mobility of the hydride was very important. So what we tried to do was we started from materials project. We started by looking at all the possible hydride, nitride compound, and then filtering them according to some criteria. For example, do we know how to synthesize this material? Are these material possible stable at the operando temperature that we want? So basically, we, starting from over 100,000 compound, we basically narrow down the number of possible hydride that we could use for doing catalytic system. Then at the end, we found 5 compounds, and for this 5 compound, we used a foundational model, MACE MP0, and we started looking at the diffusion of hydride in these 5 compounds. And basically, we found out that among these 5 compounds, there was one with a very high hydride diffusion coefficient. And we have seen that in our barium hydride compound, the diffusion of hydride was something fundamental for activating the catalyst. So from this point of view, we started by analyzing maybe a possible chemical reaction using what we have learned from barium hydride. And just recently, we discovered that another experimental group, completely independent from us, is studying the same compound, showing that it has some catalytic activity. So now we want to try to bridge the force to solve this particular process. Also, another catalytic problem another catalyst for ammonia synthesis that we have been looking in is the one that we want to try to use the proximity to phase transition basically to enhance the catalytic activity. So we start looking basically to some particular catalyst that can be a mixture of lithium and sodium liquid, and because basically with this kind of compound, we have seen that we can get the best of the two worlds. So lithium is able to decompose nitrogen, but he gets poisoned by the formation of the nitride. Instead, sodium, he can work as a catalyst, but with a very low catalytic activity because the formation of some hydride or because the bond, the nitrogen-nitrogen bond dissociation, it has a very large barrier. So what we thought was to combine the good of these two particular catalysts, and we saw that there is a beautiful physics behind it. I will not talk much about this, but basically, now we want to try to really test and improve this particular catalytic mechanism for the formation of ammonia. So as a last, let's say, message, is that if we want to design if you want to try to design a catalyst, both heterogeneous, also an enzyme we are seeing, just by looking at some idealized static structure, basically we are trying to optimizing something in which the catalyst spent the last time being. So the catalyst don't want to be a fixed structure. He is something which is dynamical, and we have to take into account the dynamics and the dynamic transformation of the catalyst if if we want to improve that. So what is our goal, let's say, is to control the catalyst dynamic to design novel structure. So our, let's say, novel design principle is to stop sculpturing some status. The catalyst is not that. We want to try to directing some movie. For example, like this is my last movie of today, is something that we can think our catalyst is a nanoparticle or a support, and the dynamical transformation will then lead to the final active phase of the catalyst that we hope, like probably the good one for the future will be something, something like that. So so of course I want to thank Michele, because when I joined the group, as a chemist with my knowledge of chemical textbook, the picture that I was getting often was a very blurry one. I was not really able, with what you learn in the chemical textbook to understand all this kind of process. But now with all this particular tool that we are trying to combine in heterogeneous catalysis, going from statistical mechanics, surface science, I feel that we are getting a more complete picture of what is really, really happening. So thank you, of course, for all this teaching. And of course, I want to thank all the group in Genova and all the fantastic guys that worked with me on this project.
Thank you. So there's time for questions.
Thanks a lot, Umberto. Really cool stuff. I have a couple of short questions. So in the case of this barium hydride, you have this sort of spontaneous surface charging with this electride formation. So I was wondering how that is sort of dependent on the size of the surface model that you choose, because I guess that you create a very polar system by having this localized electron. And the second question is in the case of this ruthenium complex, ruthenium cluster that you put on the liquid catalyst. In the movie, it seemed like the nanocluster was not that fluxional, which I would have expected to be as dynamic as the sort of surrounding environment at that given temperature. Thanks.
Okay, so I start maybe replying the second question, because I can also show you the video. Basically for that catalyst, we are exploring different size of the catalyst. This one that I show you the video is is the most stable among the small size catalysts. So this has 10 atoms, and this structure is actually very compact by itself. Instead, if you are looking to larger cluster, like a medium size, let's say 19 or 44, what we are observing in that case, that also the dynamic of the cluster is very, very important. So for example, in this case, basically, during the dynamics, you start with this cluster, with this, with this structure, and you ended up still with this structure, because basically you have just small deformation, you have some minimal deformation. Instead, if you start with a 19 atom cluster or 44, you start from the symmetric structure, the more stable one in let's say 0 Kelvin condition, but then during the dynamics you will see like a really highly fluctuating system that is also fluxional and changing very often configuration, just to optimize in that case the different interaction with the environment. So you will see a cubic structure just opening up and being very liquid also in that case. For the case of the barium hydride, in our simulation, we always try to use very large model. So basically, that can be still considered like, let's say, a local effect locally.
A very nice talk. I see there is a lot of charge transfer. I mean, charge transfer is critical in the catalytic effect. what kind of machine learning model do you use, and how confident you are that it reproduces charge transfer properly? Because it's a difficult thing to capture with machine learning.
Yes.
Potentials.
So basically let's say in this case we are using standard model. The trick that we are trying to use is just training this model with very large cutoff to learning the environment. So usually we have very large slab or very large system, and we try to use, I don't know, 8, 9 Armstrong for cutoff for the potential. So yeah, for example, MACE or DeepMD. So No, yes, but we are not, for standard, we are not using any additional term to learn long range, for example, interaction or long range correction. What we are doing, training on very large sized system and try to use the largest cutoff that we can get to retain also accuracy. And then also what we do usually is also, of course, we cannot train the potential with very expensive functional. So basically maybe what we do, we select a subset of configuration, especially along the reaction pathway, for example, and we try to validate with expensive functional, including Hartree-Fock exchange, but of course in that case we select, I don't know, 10, 20 structure along different chemical pathway, and we try to assess the accuracy of our PB, let's say, description.
Okay, good. So let's thank Umberto again. Continue with the next talk will be given by Giovanni Maria Piccini from Università di Modena, in fact. Modena and Reggio Emilia, no.
Get very upset when you miss the other part. But I'm from the Modena team, don't worry.
So here is not mirroring, of course. Let me check. Always something that doesn't work. So display.
Abbiamo stacco e riattacco.
Sì, vai. Ce n'è un'altra porta volendo. Sì, volendo c'è la HDMI. Ma non ci servirà.
Sì.
Okay. This won't work now, I guess, right? But I can stay here. Okay. So thanks a lot for the invitation and for the introduction. And let me say, it's of course a great pleasure being here celebrating Michele's 80th birthday and doing basically what I consider a family reunion with less fighting than my usual family reunions. Let's wait, it's just the first day. So before starting with the science part, let me just go down the memory lane a little and let me tell you that time has been cruel, but with me. And for this I have a footage. This is a video for the Dreyfus Prize of Michele in 2017. That's Michele, of course. The person sitting there is Daniela, with, I don't know where she is, there's there. And everything seems particularly similar to what is now. But then another character came up there, and believe it or not, that's me. If you notice something different, I can give you some more hint about that. That's me now with Michele in Oslo. So, okay, that's how it goes, but what can I do? So, moving to something that I'm a bit more confident with, apart from my personal aspect, is looking into chemical reactions. And one of the main goals of chemistry, of computational chemistry, but I would say of chemistry as a whole, is to explore the reaction network. Say, with this, I mean, you start from some reactants, your initial state, and you want to know what possible reaction product you get. And this is a sort of holy grail in chemistry because, of course, this is unknown. And this is especially important in catalysis because often in catalysis, you know where you start from. You may have some hint of what you expect to get, but what happens in between all the series of intermediate and small reactions that may be relevant to the catalytic cycle or may be detrimental to the catalytic cycles are often unknown. And if you want to use microscopic lenses in terms of, for example, atomistic simulations, if you want to do sampling with enhanced sampling techniques, for example, one of the kind of information you really need at the beginning is knowing what are your metastable states. At least have a hint of that. Why do we want to do this? Well, because the general goal is that we start from an initial state alpha, and we want to explore what goes on between the states and the other possible intermediates or product states. And why we do this? Because if we know this and we are able to sample this process, we can get information about the population of each possible other state, alpha and all the other states, and the rates that connect them. And in this way, we can build up, through a master equation, a microkinetic model, so something that informs us of the final rate at the macroscopic level. And this is a particularly daunting task. Many different techniques have been proposed to overcome these limitations, and there are two main classes of methods that can be used to explore the reaction network. One, we can call it heuristic type of methods, in which basically you use chemical intuition and chemical rules to build up a model and code it possibly to then generate new type of structures that are chemically relevant. And this goes beyond what is physically known from the potential energy surface. It comes directly from the intuition and to the knowledge that we have, the prior knowledge we have as chemists. The other class is, we can call it atomistic approach. This means that we try to walk on the potential energy surface and look for other possible local minima that may be of interest for us. So going into the history of this type of methods and the method that have inspired this new method that we proposed, this is the artificial force-induced reaction method proposed by Satoshi Maeda and Morokuma in 2010, where you basically want to find the association channel of two fragments, A and B, that form the final product A, B together. And how you do this, you take your initial potential energy surface, E, R, A, B, and you add a force that fundamentally leads to a potential energy surface that goes like a steepest descent to find the new state, which is A and B. So somehow you can apply a force in a way that along a specific reaction coordinate brings your two fragments together. The thing is that this method is a so-called static method. It doesn't imply that temperature plays a role. And we know that for many important systems, large systems, especially in catalysis, temperature, or if you want, entropy, becomes a pivotal factor in understanding and describing the process. So the idea is that moving the thing to something that allows us to sample more properly the space, and so we can go into dynamics. There are methods to do similar things, so applying a force along a variable to do this. One that I find particularly brilliant is the so-called ratchet and pole molecular dynamics, is one of the different fashions of stirred molecular dynamics method. And without going too much into the details, ratchet and pole MD works in the following way. You define a collective variable, and you apply a potential that keeps pushing in one direction, but never allows the system to go back. And in this way, you keep sampling, and at some point, you end up into the new state. And you're never allowed to go back. This is, of course, very interesting. So there's a way, a principle to push the system toward the other state, but there's a caveat. We still need to define S, which is the collective variable. And this is something that is typically not given if you want to explore a multitude of possible metastable states. In other words, what you have to do is that you need to know what A and B are a priori. And this is typically an information we are not, that we don't have. So how can we solve this in a way that allows us to not knowing, not having this information, but still finding these reaction channels? Another method proposed by Satoshi Maeda, even earlier than the AFIR method, is the so-called anharmonic downward distortion following. And I think this is a very elegant approach. Let me just try to summarize it. The idea is that you have a real potential energy surface, which is the one colored in the heat map there, that we don't know, of course, because we know that this is an unknown function. It's not a closed form that we can analytically calculate. And the idea is that you start from a minimum, and ideally you build a pure harmonic potential starting from this minimum, which is depicted with these white contours there. Then you look at the variation of your potential energy surface with respect to the ideal harmonic functions. The maxima along this function here represents the direction of maximal anharmonicity. And this you assume to be the reaction channels, because where you have a large anharmonicity means that in this direction you have a sort of a slowest ascent to find another state. So if we want to translate this into sampling terms, we need to go back to the fact that now we need to include temperature, because we live in a finite temperature world. So we need to shift from a description that goes from potentials to something that goes into a probability distribution. So how can we do this? And this is something that has been bugging me as an idea for many years, and I was struggling in somehow finding a way to formalize it. So how I came up to describe this? Well, let's think of having a simple double well potential, a symmetric double well potential. If we imagine that we are in the minimum and we do a harmonic approximation of our minimum there, and we sample, we do some canonical sampling in this minimum there, what we get as probability distribution of this, we get a Gaussian, right? So the probability distribution of a harmonic potential in the canonical ensemble is a Gaussian function, which is centered on the minimum, and it's perfectly symmetric. But if instead you run dynamics on the real potential, you start to observe something different. You start to observe an asymmetry of the distribution. And this can be described by the third moment of the distribution, which is skewness, that tells you if you have a positive tail of this distribution, that's the direction where your potential starts to be softer, so to say. So that's the direction where you want to go. Imagine that you're blind, you are working in this potential in one dimension, and you don't know if you have to go left or right. Well, following this information you get from a very limited information that you have from the sampling of the minimum, you can actually then apply a bias in the form, like, for example, of ratchet and pole, so half harmonic potential, and keep pushing to the other state. So we named this method loxodynamics, and I asked Wanda, I thank Wanda for because she proofread my possible invention of this name. And believe me, this works perfectly.
You can.
All right. Can you hear me if I talk like that? Yeah. Is it microphone? Okay. Again? Okay. Okay. No. I guess it works now. Yeah. Okay. Fine. So, but of course, there's a problem. Calculating skewness in one dimension, it's very easy. It's a closed form. It's analytical. When you go to higher dimension, this becomes extremely complex, and typically it doesn't yield very clear results if you don't sample a lot. And we don't want to sample a lot. We just want to have minimal information. So to solve this issue, we reverted to the use of neural networks in the form of an autoencoder, where we use the autoencoder to transform a large set of variables, because this is typically what we have in chemistry. We have a lot of information. We have many descriptors, and compress them into one single, one-dimensional latent space where we can easily calculate the skewness. And once we do this, we can do another thing. While we minimize the loss for the autoencoder, which allows us to reproduce exactly what we get in input and output. In the latent space, we can maximize the skewness. In this way, we can actually try to push even better into the direction where the skewness is maximal. So let's see if it works. Let's go into something that is more than one dimension, and without so much complexity, we go into D. We take this potential where we have two minima that are connected by two pathways, and our expectation is that we follow the one that has the largest anharmonicity, which is the left bottom one. And if you start sampling this, and you just keep collecting some information cycle after by cycle, at some point you start to reach the transition region, and you end up into the other state. And believe me, if you start from that state, then you can go back to the other one. And if you push with stronger biases, you can also explore the other state. Then we started looking at something a bit more complex, so a real chemical reaction. This is a prototypical chemical reaction. It's an asymmetric nucleophilic substitution where we substitute the two halides in the, for the carbon atom. And we took two dummy descriptors, the two distances between the carbon atoms and chloride and fluoride. So this is rather simple, it's trivial, but we look at both the forward and reverse reaction. We start from one state for both reactants and products, and by keep sampling and gathering information, we are able to get to the new state and basically observe the same process. These are two independent processes. Then we keep complicating and getting a bit more complex, and we look into another textbook example of organic chemistry, which is the Diels-Alder reaction. Here, to make the life more complicated to our method, we took all the possible distances among carbon atoms. And this is, of course, can be dangerous because you can end up chemically in other possible states that are not the lowest lying path, that is the formation of the Diels-Alder combination. So if you look at this and you start from the reactants, which are ethylene and butadiene, you start there, you start exploring, and of course you are exploring also all the conformational freedom of the two fragments. At some point, following the direction of maximal skewness, you start to align conformationally the two fragments, and by pushing further with the bias, you end up forming the final state. What happens if you do reverse? The reverse is even more complicated if you think about it, because now we have to be extremely selective in breaking the two sigma bonds that have formed after the reaction, and the basing is very symmetric. There are very small variations. I mean, the anharmonicity comes from the fact that two sigma bonds vibrate a bit more than the other pi or not reacting sigma bond. Nonetheless, since the method is not brute force, it's extremely delicate, so to say, in doing this, we can realign the fragments in order that they leave each other, and then you form the two products. So far, so good. This is gas phase chemistry, but let's see if this can be applied to catalysis. And we run into something that I'm very used to it, which is zeolite catalysis. And this is a class of reactions that in catalysis are extremely important from the technological point of view because they are very useful in terms of feedstock, which relates to dehydration of alcohols in zeolites. So we started with a very classical case, which is ethanol dehydration in acidic chabazite. We included many distances, both light atoms and heavy atoms, both from the substrate and both from the framework. And we started looking at it. So we start from the original adsorbed complex, which is methanol adsorbed on the Bronsted acidic site. We keep pushing gently, and after we have gathered some information, we start to see the reaction happening. So water is detached, and you have this complex where a proton is abstracted from this methyl group and goes back to the catalyst, forming ethylene. And so we were very happy. There's a double bond missing there. We were very happy. And we said, okay, that's fine, we got it. But then my student came up and said, look, I'm finding something different that I was not expecting, but apparently it's a very well-known mechanism. You start from this one, and while you eliminate water, instead of having this carbocation that is deprived of one proton, the carbocation connects directly to the framework. And this is a so-called atoxy species, which can also be spectroscopically identified in some long-lived intermediate states. So we end up there, and we said, okay, how do we go back, how do we recollect the real product? So we applied a penalty function to prevent the system going back. And if you keep pushing, following the same approach, using the same set of variables that we used at the beginning, you are still able to recollect the final product. So in this way, we rebuilt the simple but not the trivial chemical reaction network of this type of reaction. But then if you just take something a bit more complicated, which is butanol and not ethanol, so you add 2 more carbon atoms, then here you may have a plethora of possible stable state intermediates, or also states that may poison or kill the catalyst. And this is actually what we observe. We start from the adsorbed butanol at the Bronsted acidic site, and we observe what we expect. We expect 1-butene, fine. But then actually you can also get the double bond in the middle, and we observe both cis-butene and trans-2-butene. And then we observe other exotic states, like, for example, we see that we have the butoxy formation at the Bronsted site, but this breaks the Bronsted site. And this is a mechanism that in zeolites lead you to the so-called extra aluminum, extra framework aluminum species, or deactivation of the Bronsted site, because the aluminum site is hydrolyzed by the reaction. And this is a typical poisoning mechanism in zeolites. Or you can find that the butoxy species is formed away from the Bronsted site. And from these states, basically, you can proceed further to reach the products that you want, because basically you are killing the catalyst. And we are observing this, and this is, I want to stress, we give no prior information on this. This is totally found blinded. The only information we provide is a set of redundant distances that may be chemically relevant. So here we use like 80 distances. So there's not much human bias in that. And so we are planning to expand this. We will look into something that can somehow act more autonomously to do this type of exploration, and we want to apply it to different types of chemically interesting scenarios, whether it is enzymatic catalysis or, for example, prebiotic chemistry, which is very simple from the point of view of the substrate you have, but very complex in the outcome, as well as heterogeneous catalysis or combustion chemistry, pyrolysis, and many other type of examples. So with this, I would like to thank the people that work with it, especially Qikun Zhang, which is the PhD student that still works with me at RVTA. And I would like to focus your attention on both Alessandro's and Chintu's poster at the poster session, all the funding that we received, and of course, you for your attention.
Thank you also for being perfect time. You're making my life very easy, both.
Thank you, very nice talk. And I was interested to know have you tried using this skewness type of collective variable for sampling back and forth transition and converging free energy landscape rather than just exploring reactions?
So yeah, I should have a backup on this, at least for the model potentials. Let's see if my computer reacts. No, I may have canceled before. So anyway, to answer your question, yes. For the model potential, we can directly map them, and we see that they actually follow what we expect as a proper foliation of the path. So you see directly the progression of the collective variable. And if you have different pathways, you can actually learn the collective variable that is selective for each specific pathway. So for model potentials, this works really well. For the reactions, it works. You can sample. It's not an optimal CV, but it's clearly understandable why. It's because you learn a lot of information while you escape one state, but once you reach the other state, you stop. So it doesn't learn much of the process of how it is to be in the new product state and how to go back. Because the process is unilateral, so you go into one direction and then you stop and eventually restart from there. But in principle, they do, and they do a pretty decent job. You can converge free energy surfaces. Concerning the efficiency, I wouldn't say they are not optimal. I'm totally honest with that.
Other questions? Actually, I have a related question. So when you jump to a new state, you start training from scratch, a new model, right? Correct. You completely forget.
Yeah, exactly. So there's the process starts like that. We use warm starting, so for calculating the part of the autoencoder that is really the autoencoder, we collect all the information, so we have a global data set that is kept, we keep accumulating during the simulation. Then skewness is maximized at every step. Once we reach a new state, we reinitialize the network and we start over. Otherwise, we noticed, we tried to explore that, but it was just making the learning process much, much slower.
And how do you know that you are in a new metastable state?
That's a very good question. So we use a set of rules that are based, for example, on topology, adjacency matrix, or other type of similarity measurements that allows us to understand that we end up in a new state because we have changed the topology of the bonding.
Yeah, thank you for this talk. In the beginning, you showed the famous volcano plot, right?
No, it wasn't me showing the volcano plot.
Okay, there was a volcano plot, sorry. Is it possible to come up with something so visual and quantitative in this dynamical way of looking at things?
Well, it could be, in principle, because so the plan, the goal, the final goal is to find a way to map whatever we have, which is, of course, in high dimensions, into something that is reduced dimensions. So possibly dimensionality reductions approach may help in visualizing the final chemical reaction network, but I didn't start to explore any of these possibilities. So I don't know if this answers your questions, but at the moment I have not a clear idea of how one can do actually that.
Can I make some propaganda?
Of course.
Last year or 2 years ago, we published together with a group in Tel Aviv University a method that where from the dynamics, the way the wiggle or some CV or some coordinate, you can identify the different metastable state kind of automatically. It's called, I think, BEAST or something. Yeah. Okay, cool. So BEAST to you.
Sure.
Good, so if there are no more questions, I think we can thank again Giovanni Maria.
That's it.
And the next talk will be given by Tarak Karmakar from IIT, not IIT Genova, but IIT New Delhi.
Thank you. Is it a problem? Okay. It's great to be here. So I already told a few of those my friends that we are back to the family. Thanks, Michele, to build a family. So eventually, first of all, I thank the organizers for, especially Ali, for inviting me here, and I'm enjoying this meeting. And it's kind of a, for me, it's much easier to talk about data efficient deep learning, since Luigi, I mean, it started with Pablo, and then Luigi, Umberto, they kind of covered all the stuff. And so what I'm going to do is to give you a kind of a different flavor of machine learning potential, or what we tried to do, or rather attempted to do. And then show some examples where we can apply this kind of method to deal with complex systems, starting from, let's say, starting chemical reaction, phase transitions, to understanding gas adsorption in framework solids. Okay. Oops. Now it works. Yeah. Thanks. Somehow this pointer. Yeah, so before I discuss today's topics, I just wanted to flash a few things. So we are mostly developing methods related to structure property prediction, and then mostly utilizing the graph neural network. And recently we have done one work on graph coarsening to develop coarse-grained models and apply them to nano kind of biosystems. And then a lot of our work is mostly focused on developing machine learning potential for reactive system, including catalysis. So you've heard a lot of about catalysis. So today I'll be talking about the right side of it. Let's say the machine learning potential. This slide does not need any, let's say, description for now, because you have already heard from at least 3 speakers about the seminal work by Bella and Parrinello, 2007, and then after 1 decade, this work by Roberto Carr and Winan. And then after this, there was kind of an explosion of machine learning potential, different methods and different applications. So what we were trying to do is, our first attempt in dealing with machine learning potential was to model chemical reaction in explicit solvent. So we took a very simple chemical reaction, which is typically SN2, Mansutkin reaction in explicit water. And then we realized that to model this one using a kind of a standard deep MD protocol, we needed something like 500,000 data points, which was huge. And then we realized that probably if we try to think of a method by which we can reduce the data, then our life would be easier. And I was telling Luigi that probably my talk should have been before you, because Luigi's method is kind of, it reduces the data to hundreds of data points. But yeah, my method is kind of still we are stuck at the 1,000 data points. But the kind of approach that we took here is called locality sensitive hashing. That means you start with a lot of configurations, so each circle kind of indicates one configuration, and then try to find out similarities between these configurations and then put them into buckets, right? And we wanted to see the things at the atomic level, so that means we zoom in to the atoms and try to find out its neighbors, and depending on that, in a reduced dimensional space, we try to identify what are the configurations that can be put in one bucket. And eventually, after doing that, what we managed to get some data points which are quite diverse, and then we train our machine learning model to get the machine learning potential. So when we deal with, let's say, atoms, so then there is a problem of higher dimension. So we describe the environment of an atom using the famous SOAP descriptors, but the problem was the dimensionality. And so high dimension makes the comparison much better, but then dealing with high dimension is kind of impractical. Then we found out there is a way out, and there's a kind of a, we call it, there's a JL lemma which says that for any set A of n points in a high dimensional space, there exists a linear function that maps the points to a lower dimensional space, which approximately preserving the distance between them. And that kind of helped us to design the method by which we could reduce the data size. So here is our protocol. So we start with, let's say, defining the descriptors, SOAP descriptors for each atom, and then and thereby we got the SOAP matrix, which is n cross d dimension, and then from there we kind of created configuration vector by flattening those individual atomistic SOAP descriptor, and then the configuration vector we stacked them row wise to create the configuration matrix, which is the capital C. And then again, the problem with this one is you still have a large dimension, so we applied principal component analysis. Is the pointer working? No, this is not. Anyway, so what we're doing here is we apply the principal component analysis to go from configuration matrix to a reduced configurational matrix. And then here we define something called projection matrix, whose elements are derived from, let's say, normal distribution. And from there, we go to projection matrix, this one. And finally, we apply hashing on the elements of the position matrix. Eventually, end up getting some numbers which is tagged with each configuration. And then, based on that number, we kind of put the configurations in different buckets. And that's how we kind of filter the similar configurations. Now what we did in our modified workflow, we have incorporated that locality sensitive hashing to filter the data before we go to the active learning, that DPMD protocol. Now with this method, we applied again, so we kind of revisited the chemical reaction modeling, and now it turned out that we could deal with this same system with, let's say, almost 20,000 of data points and got the similar kind of free energy surface. And that was useful to understand the role of explicit solvent in chemical reaction in the condense phase. And then we went ahead to model phase transitions. A typical example is like sodium chloride going from the liquid state to the solid state. And we started nucleation in solvent, in explicit solvent. We applied our method to, let's say, modeling catalysis. We have heard a lot about it. And then another interesting example is gas diffusion in framework solids. Yeah, I mean, this is just to show you that our method did pretty well in terms of predicting, let's say, the thermodynamics and to some extent the barrier. And we compared with, although there is not exact mapping from the experimental value, there's a little different system, but we are somewhere close to the numbers. And then this is sodium chloride crystallization from molten state. And in this particular case, we used a collective variable, which we developed during my postdoc with Michele in Lugano. So this is based on taking structure factors of sodium chloride, three-dimensional structure factor, and we bias them. And first we calculate for sodium and chloride, and then we linearly combine them to get the overall CV, and we biased it to understand the solid-liquid transition. In principle, one can do take the help of nonlinear dimensional reduction as well. So the model did pretty well in terms of giving us the free energy profiles at different temperatures. And we checked the convergence also, and it's kind of pretty fine. We are still off in terms of predicting the melting point. There could be reasons because of finite size. We didn't incorporate the long-range electrostatics. Those are limitations, but probably in the upcoming work, we probably deal with those kind of stuff. So here is another application where we try to model nucleation of something called Nanocluster, which is atomically precise metal nanocluster, which is an emerging class of nanomaterials which has diverse applications in nanoscience. So we first developed the machine learning model and then started using very simple collective variable, coordination number based collective variable. We model how the nanocluster forms in methanol. So here is the movie. So again, we kind of got some tens of nanoseconds of trajectory, but here I'm just showing one transition where, from randomly dispersed, atoms, gold atoms, and kind of organic linkers, we get this nanocluster nucleated to a star-like shape like this one. Now we kind of zoomed in and tried to understand how the nanocluster forms. So apparently, first it forms dimer, and three dimers, they come together to form the star-like, the nanocluster Ag6L6. And we could calculate the free energy surface as well. And eventually, from the free energy surface, one can understand the role of solvent as well. Now, catalysis on magnesium oxide surface. So this is kind of our first attempt to model heterogeneous catalysis. And so we took an example which has already been studied in the past by many groups, and there are a lot of DFT calculations as well as AIMD simulations, which revealed eventually the mechanism and everything about this system. But we thought, okay, let's try to revisit this with machine learning potential and try to find out something which was missing probably from the DFT calculations. So this is our system under study. We have magnesium oxide surface, and we have a nanocluster, which is AU8 gold nanocluster. And what we did, we created one epicenter defect, which is shown by this blue square, where we have removed one oxygen and created this epicenter defect. And we wanted to see, if we create the defect, how it affects the dynamics of the nanocluster. And that's how we found very interesting stuff, particularly for this system, which was kind of somehow missed by static DFT calculations or short AIMD simulations. What we found is this. Now, nanocluster, when we put on top of this defect surface, it gets anchored to the epicenter defect site by, let's say, one gold atom gets anchored there, and the nanocluster is highly dynamic. And most of the times it attains or it remains in the flat conformation, which was not the case in DFT calculations or short AIMD simulations, because eventually if you run tens of picoseconds, you may get stuck in one of the local minimum. And then what we did is we calculated the free energy surface. We found out which conformation kind of dominates during this process, and we found out these two conformations, they mostly kind of having the kind of lower free energy minimum. And the other one, which are kind of three-dimensional, they are short-lived. So this is an interesting thing that came out from our simulations. Then we went ahead to understand or to model the CO oxidation. So this is like, you have the CO and oxygen, they couple together and then form CO2, and one oxygen remains there. In the next cycle, it again forms CO2. Now, so we did it by step. First, we added carbon monoxide, and then we saw something interesting stuff, that carbon gets attached to one of those peripheral gold atom, and we found out there's a kind of a charge redistribution that takes place, which is dynamic, and that allows the carbon monoxide to get localized in near one peripheral gold atom. And then we thought, okay, that's the end of the story, and we submitted the paper. We somehow missed a lot of interesting stuff, and then the reviewer told us that probably we missed a bigger picture of it. More important one is oxygen attachment to the gold nanocluster, which is actually in which the charge transfer is more prominent than CO. So then we modeled the whole chemical reaction. We thought, let's give it a shot and try to model the whole chemical reaction and see how it happens. Then what we observed is this. So CO gets anchored to one of the peripheral gold. Oxygen, on the other hand, is also kind of anchored to two gold atoms, as well as the magnesium at the bottom. So it's a perfect localization of the reactant in proximity. And then eventually what happens is carbon monoxide approaches and the reaction takes place, and one of the oxygen gets, in the product state, it gets stuck to attach to the magnesium, and in the next cycle another carbon monoxide comes and the reaction goes on. And then we kind of mapped the free energy surface or calculated the free energy surface, and what we found is, again an interesting observation. If you follow the free energy surface on left hand side top, we started from A, which is the reactant state, and then instead of following a diagonal kind of path, initially it went A to B, which is the elongation of oxygen-oxygen bond. So that means the elongation of the oxygen-oxygen bond, takes place first, followed by, the attachment of CO to one of the oxygen, and it forms the carbon dioxide. And there's a huge charge redistribution or charge transfer takes place during the reaction, and what we found is the charge redistribution or charge transfer is actually the driving force for this reaction to happen. Again, so here I am again being a little cautious about, already we had some discussion about dealing with charges with this kind of model, but we are kind of qualitatively predicting the free energy surface and all, but in principle one has to pay extra attention to charge transfer in machine learning model. And then we went ahead and calculated the density of states as well as this IPR, inverse participation ratio. We found out that as we go from epicenter defect magnesium oxide and then we added the nanocluster, the Fermi levels are getting populated. So we're getting more and more populated states at the Fermi level, and that is actually triggering, if you follow gradually from top to bottom, we added carbon monoxide, and then we have added oxygen, and look at the Fermi level. Things are getting populated heavily. And that's how we could find out some additional information by doing this kind of modeling. So the last example is in which we model the structure and dynamics of, we have studied structure and dynamics of nanocluster organic frameworks and gas diffusion. So you have heard of metal organic frameworks and covalent organic frameworks, MOFs and COFs. But this is another new, let's say, emerging class of materials. It's called nanocluster organic framework. In short, it's called NOF, because you replace the metal centers by nanoclusters, and that's how the name came. So what are the things that we wanted to address by developing machine learning potential is, classically, you cannot model this kind of system because you don't have classical force field. So as soon as you try to do something on the empirical force field, then the nanocluster, the total framework collapses. Then we thought, okay, let's try to do this using machine learning potential. And we started with some AI-NV simulations, and then we applied our LSH, and iteratively we constructed the ML potential, and that allowed us to model flexible NOFs. And then we went ahead to study oxygen diffusion inside the nanopores, and then try to understand thermodynamics and kinetics. And this class of materials are very promising for catalysis. So our next step is to study catalysis inside these framework solids. Now, if you look at the structures, then you probably see the nodes that I am calling is on the right-hand side. That node is a nanocluster connected by linkers, and that's how you get this framework solid. And we have a bipyridine linker here. And an interesting thing about bipyridine is these guys keep on moving like this, which was, if you do a normal DFT calculation or even short AIMD, probably miss this kind of motion, which is very important for the oxygen gas or any gas diffusion inside the pores. Right? And we kind of followed a standard protocol in developing this machine learning potential. And what we found is something like this. It's a periodic. You can, in principle, go and extend it as much as you want. And then you look at the oxygen, how it is diffusing. An interesting thing about this material is it has two-dimensional pores. So, we need to design some collective variable that allows the oxygen to sample on two dimensions, x and y. And then we mapped its kind of trajectory. If you look at the red dots on left-hand side top, and these are kind of layer by layer. Oxygen diffuses on x, y, and it kind of explores everywhere. And then we projected that one on the collective variable that we have biased, and we found an interesting, very symmetric free energy surface. And from one pore to another pore, there's a kind of a barrier. So it kind of hops from different pore sites. Yeah. Now, so there are a few things that we kind of learned from our, again, so these are kind of early attempts in modeling diverse set of materials, starting from chemical reactions to complex solids. We learned few things that, okay, we are still, we could reduce it from 500,000 to 20,000 data points, but Luigi eventually will tell me that, okay, look, 20,000 is where we start, right? But again, so this is for a system where the configuration space is quite huge. It's a chemical reaction where the reactants may diffuse, product may diffuse anywhere, and the environments keep on changing during the reaction. But we feel that 20,000 is still not bad. But for solids, the kind of example that we gave for sodium chloride or even framework solids, we could reduce it to something like 1,000 configurations. You take 1,000 configurations, train the model, and then you can run whatever things you want, gas adsorption or separation. LHH-based filtering is good for filtering the data and for efficient training, but the problem with this one is we are still doing it outside of the active learning loop. So our next attempt would be to integrate this method inside the active learning so that whenever we generate the data, we apply this hashing-based technique to filter it on the fly, and that would probably help us to get rid of generating excessive data. And then the known problems that is related to electrostatics and charge transfer, we are again trying to switch to some other, maybe dealing with some symmetry functions. But for now, as Umberto said, we are just dealing with this system by taking larger cutoff for our system. Also, we have noticed that for the sodium chloride and those kind of system, it is important to have those little tweaks that we do for now. So this is my group, and the work that I have discussed are mostly done by these people. All of them are graduate students. And just 1 minute to tell something about my story. Okay, so the first one is a little scary. So during COVID time, my passport was getting expired. Okay, so everybody talked about Michele's academic side. I'm talking about Michele as a savior, right? So that was a situation where the flights were kind of getting cancelled every now and then. So I was stuck, and we had to move from Lugano to Genova. Whole team moved except me, so I was there alone. And then Michele wrote to embassy and did kind of a magic, okay, to help me get my passport renewed. And they drove me to Genova, to the hotel, okay. So that's the human side of Michele, which really touched me. And then I kind of try to, learn from Michele this side of it and try to replicate. And then another incident is when I got my job offer from IIT Delhi. So we were in the Mensa eating food. And I told Michele that, Michele, I got the offer. And I've seen that guy jumping out of the chair and doing like this in front of the crowd. And that's Michele, right? And then I asked Michele a few questions, and we used to discuss a lot of things. And I asked Michele, how do you manage to build such a wonderful group? Michele might not remember this conversation, but again, as a professor, I hire some good people. Okay, so that I really value, because more than talents and blah blah things, I try to hire good people, and so far we managed to get a good group. And Michele visited us last year in February, and these are glimpses of that visit. On the left and top side, probably you see the Michele's funny side of it. He took a picture with our Prime Minister, the model with Modi, okay, not the real one. Yes. So with this, thank you, Professor, for everything you did to me. I had an amazing time, and career path changed. I met Michele in Lugano 2015. I made a wish that I wish I could work with Michele. Somehow it happened. And from then, life has changed. So thank you for everything. Thank you all. And happy birthday, Michele.
Thank you. There's time for questions. Ali?
So thanks very much for the very interesting talk. So I know people have asked this question about the role of charge transfer. And so I can understand from a mechanistic point of view that there's some charge transfer going on, but so charge transfer, as far as I think about it, is a fast degree of freedom.
Yes.
So, but why is it relevant for the quality of the potential? I mean, if you've gotten to whatever level of electronic structure theory correct, you've got the energies, you've got the forces, so isn't the charge transfer sort of encoded in there? Why is it important?
Yeah.
Apart from a mechanistic chemist point of view.
Yeah, so in principle, when you develop the model, intrinsically it is included. But then when it comes to, let's say, if you zoom into some transition states or the configurations where things are happening at the transition state, where the charge transfer is very, very crucial, and then people often discuss whether our model is taking care of that. So that's a question that the community kind of is going after. But I believe whatever you said is already included. So I think we're safe in terms of dealing with it. We don't need to do much things, but if one wants to refine it further, then probably we need to include the stuff, which Pablo also discussed. Yeah.
Other questions or comments? I have actually a curiosity also related to the previous talk. So you mentioned about this decrease in the number of points, but how important is the quality of the ab initio calculations for the this type of applications?
Yeah, so eventually, let's say we run quite a few ab initio calculations at different temperatures to sample the phase space, and then we do the filtering. So often we run multi-temperature, all multi-canonical or multi-temperature pressure to sample the phase space, and then we filter it. Because eventually, even if you run AIMD simulations at any level, let's say you think about functional and all, you create some structures which are kind of correlated. So you just want to get rid of those correlated configurations and get a diverse set. Instead of choosing dense states, you start collecting points from entire phase space. Yeah.
Okay, so if there are no more questions, so it's time for a coffee break, which will be in the terrace again, and we will reconvene. Let's thank all the speakers again.
Thank you. Thank you, everyone.
So, good afternoon, everybody. I suggest you started... Giulia Galli was supposed to be the chair, but she has an unexpected commitment, so I'm Laura Gagliardi, I'm replacing her. I'm from Bologna, she's from Modena, so it's almost the same thing. And Galli, Gagliardi, you Chicago. Well, I'm excited to chair this session, and the first speaker is Ursula Roslisberger from EPFL. Ursula, the floor is yours.
Can you hear me now? Okay. Well, it's of course really a special pleasure to be here to celebrate with all of you and of course with Michele his 80th birthday, and I decided to show you some of our work that we use different types of computer simulations to really understand the kind of fundamental, atomistic, mechanistic origins of some of the processes that underlie the functioning of solid-state solar cells. But before I get to that, so allow me share with you some of the memories. Oops. Not yet. So I know Michele since really long time, almost 40 years. So I got to know him at IBM, where I had just started a PhD in 1987, so 2 years after the publication of the Parrinello method. I was working with Wanda Andreoni at the time, and then Michele joined IBM, so I got to know him, and we also worked together. And then, after my PhD, I left and I made a postdoc with Michael Klein, and then returned actually back to Europe to spend another year with Michele at the MPI. Okay, I guess this doesn't really work. MPI in Stuttgart, before we ultimately both moved back to Switzerland, not quite at the same place, but we had certainly opportunities to see each other and also do some collaborations. And also see each other, of course, at many different conferences and many nice occasions, and this was certainly one of the memorable ones. So you have maybe guessed, so this behind is not the Max Planck Institute, so this was from a trip that Paolo Carloni organized, where we went to Vietnam and had also a trip to Cambodia, and this is Angkor Wat, so that was really nice trip together. Okay, so let me start with the science. So we all know Michele really loves methods, and he has made so many contributions, so this is really a kind of super short list of this. But he not only kind of develops methods from an aesthetic point of view to have another elegant method, but we all know, and we've seen so many examples already at the conference, these are really methods that now enable us to tackle really complex problems and hopefully make some practical impact. And certainly for the things that I'm going to show you today, it would have been impossible without many of his contributions, from the basic MD algorithm with early on, together with Rahman, with the flexible cell dynamics, then of course Parrinello dynamics and implementation in CPMD and CP2K packages, but also combination with enhanced sampling, with metadynamics in all different kind of variations. And of course, we all know that early on, when nobody really was, or at least there was much before the general hype in machine learning potentials, that Michele already had suggested the use of neural networks for MLP potentials. And of course also all the recent combinations also in the kind of synergistic use of enhanced sampling methods with neural network potentials. All these are really kind of super useful tools. Okay, so certainly, as I mentioned, for the type of problems that we are trying to tackle, these methods are really essential. And okay, I think all of you know probably about lead halide-based solar cells. So they really are the kind of most quickly developing solar cell technology. So they started early on in 2000 with a very small photoconversion efficiency of a few percent. In only 8 years, this had already increased to over 20%, actually already higher than the kind of market leader in polycrystalline silicon cells. And I think the current record, and this is almost changing by the day or week, is actually right now at almost 27%. So that's getting very close to the theoretical limit of single junction solar cells, about 33%. Okay, so the general kind of device in the normal configuration of lead halide perovskite solar cells is depicted here. So you have the photoactive perovskite layer that is sandwiched in between two layers that are selective charge carriers, the electron and the hole transporting layers, that then are connected to electrodes, one transparent electron, so that you can shine light from the top here. And okay, the perovskite material, of course, has the typical ABX3 structure. So you have a divalent cation that is usually indeed lead, that is here at the center of an octahedron, at which you find a halide ion, mostly iodide, but also sometimes mixtures, bromide and iodide here at the corner of the octahedron. And then you have a monovalent cation that completes this kind of cubic type structure. Now for this monovalent cation, you have some choices. You can have either fully inorganic ions like cesium, or you can have organic cations like methylammonium or formamidinium cations. And okay, this kind of really quick evolution is really due to the very special and favorable properties of the photoactive perovskite layer. So you have a broad absorption spectrum, you have band gaps that are very close to the optimum band gap, and they're also highly tunable by mixing different halides, or by changing the cation, you can actually tune the band gap over wide ranges. And they're also excellent charge carrier, both for electrons and holes with very long diffusion lengths. And on top of all that, they are kind of like really easy to make and very cheap to make. Now, a lot of these type of properties are actually due to the special structure, but also due to the special electronic structures of this material. So you can see here that, okay, in a perfectly cubic perovskite structure, you have this octahedron that are sharing corners, so you build kind of a three-dimensional, fully connecting network through space. And indeed, in terms of the electronic structure, is really due to kind of a special alignment, a special resonance between the orbitals of the iodide anions and the lead. So both top of the valence and conduction band are made up of lead and halide orbitals. Here you see the top of the valence, so you see pretty surprising for top of the valence is actually an antibonding state, where you have p-type orbitals on the halide and you have s-type orbitals on the lead. Okay, so indeed all these kind of advances were made by different contributions. Many people are working in this field. And some of the advance was really coming through compositional engineering. So can I modify the composition with mixing cations, with mixing anions, with having maybe other elements that can be incorporated. But I would say probably the biggest part came from indeed varying the preparation procedures. And I said they're easy to make, but you can have many different conditions that actually lead to better quality crystals. And also very important, and this is one of the most active fields, certainly also at the moment, is interfacial engineering. You can see, okay, these are thin film solar cells, so you have many different materials put on top of each other, and each time you have an interface, and to control this interface and what is happening there can be a challenge, and this is certainly a lot of the kind of improvement also comes from the engineering of these interfaces. So in spite of that, okay, they have very high efficiency right now for lab-type devices that are usually pretty small still, so they have to be scaled up, and there will be also kind of reduction a bit in efficiency, so the kind of search for even higher efficiency is still going on, but many of the efforts nowadays are also for higher stability. And okay, the two actually go a little bit together, hand in hand. Often if you have higher efficiency devices, they are also more stable. And stability is a kind of complex process in this context, so there are many different types of stability. So some of the most successful materials actually are polymorph, and they exist in a photoinactive form and a photoactive form. And unfortunately, the photoinactive form is the thermodynamically most stable form at room temperature. So you kind of fight a constant fight against thermodynamics because you want actually the photoactive form in your device. Then there's also thermostability. So many of the organic cations actually have a tendency to, or some have a tendency to decompose at higher temperature. And also really under operation condition, photostability can play a role. So with the photoexcitation, you usually have a charge transfer from the halide to the metal ion, can lead to actually oxidation of the iodide to I0, and then you lose it from the lattice, or to reduction of the lead to metallic lead. And then, of course, these are really ionic solids, so they are salts. So if you bring them in contact with water, you dissolve the crystal. And, of course, also defect formation, and also linked to that, once you have defects in the lattice, you open up ionic migration pathways. So all these can contribute to the kind of still limited stability of these devices. And many people are really working on that. And one other issue is, of course, also environmental compatibility. It would be nicer to have lead-free devices, and also there the search is really actively going on. So as I said, we really make use of many of these. So we often use classical molecular dynamics to have a first kind of wider scan of all possible configuration, because often we don't have really much structural information, especially about interfaces. And we use, of course, static DFT, but also really a lot of Parrinello molecular dynamics in combination also with enhanced sampling and, of course, machine learning potentials. So indeed, as I said, classical simulation, so we actually use both machine learning potentials with different approaches. We have a kernel-based and a neural network-based approach, but we also use, because we generate anyway the data for training, we also use the same training data for actually automatically parameterizing analytic force fields, and both polarizable and non-polarizable force fields. And okay, there are the pros and the cons for both. So in terms of force fields, Analytic force fields have fewer parameters, they're less data hungry, so often you can fit them with less data. They're, of course, more limited in the accuracy. They have a more stricter, less flexible form. But we can often also learn something about the underlying physics that sometimes is more difficult to really get from the neural networks. On the other hand, machine learning potentials, of course, are really more transferable. It's super hard to have one general universal force field that can describe the bulk perovskites in different composition and then different surface cuts. It's impossible to have always charge neutrality if you cannot adjust the charges. So I would say, you know, we kind of use whatever can give us some information. So just to give you an example, indeed, about physical insight, I mentioned these two phases, the photoactive perovskite phase here, nicely cubic phase, and the thermodynamic most stable phase at room temperature, the delta phase. You can see here, instead of having corner sharing octahedron, here we have actually phase sharing octahedron, and you don't have this kind of fully connected 3D network. And by comparing, for example, polarizable with non-polarizable force fields, we were asking ourselves, okay, what makes this delta phase more stable than the alpha phase? What are we fighting against here when we want to stabilize the perovskite phase? And indeed, turns out that the permanent electrostatics will be largely in favor of the perovskite phase. But, okay, the delta phase actually wins via the polarizations or the induced dipole contribution. And that's pretty clear when you look at this because, okay, the alpha phase, the fully cubic alpha phase is highly symmetric. So actually the polarization contribution, induced dipoles cancel each other completely out. So you have zero polarization stabilization. Instead, the anisotropic delta phase indeed has already a quite sizable contribution at a lower temperature. Okay, so if we want to kind of contribute to the search of better materials and better devices, we really have to be able to tackle the kind of strategies that are used, so compositional engineering, but especially also preparation, procedures, and interfacial engineering. And concerning, say, the preparation, as I said, it's actually in principle very easily done in the lab. So these are some students, undergraduates who are actually gymnasium level students that come to visit the labs of Michael Gretzel every year, and they can prepare their own perovskite solar cells. So it's not easy to do it. It's not so easy to do it in a reproducible way, but you can kind of make your solar cell rather easily. And there are two main kind of preparation procedure. One is called the so-called one-step procedure, where you directly put all the ingredients, so lead iodide plus, say, formalinium iodide, into a solvent, usually solvent mixture, and then, okay, you use this mixture and you spin coat it, so you put it on a rotating disc, and due to the centrifugal forces, the solvent is actually evaporated, and often use also other anti-solvents, so solvents where the ions would be less soluble to help crystallization. The other one is the so-called sequential two-step process, where you actually start with solid lead iodide, which is this layered structure here, made up of this shared octahedrons, and you soak this into a solution of the monovalent cation, so formalinium iodide, and this actually is transferring to the perovskite structure. Usually you have to heat it up, and then, okay, you can get the perovskite structure. So, okay, if we want to understand how this can be modified, what are better conditions, there are a lot of additional things added to these preparation conditions. If you want to understand this, we really have to be able to tackle how these materials are formed and how they nucleate and how the crystals are growing. And of course, all of you know that looking at nucleation and crystal growth is a super difficult problem. We saw some beautiful examples this morning, Pablo. So to do this for multi-component system with 3 different ions in a solvent mixture was pretty much kind of looking like Mission Impossible. But I showed you here the movie, so I wouldn't show you the movie if it would not have been working out at some point. But certainly was a very challenging problem. But we learned also from other members of the Parrinello family that Michele always encouraged us not to shy back from difficult problems. So we tried this. We only dared this, of course, together with Michele and also with the help of Pablo and my PhD student at the time, Paramveer Alwat. We tried to do metadynamic simulations of this homogeneous nucleation, so the one-step process. And after trying many different collective variables and so on, it finally worked out, and we could understand, certainly on a qualitative level, what are the different kind of important steps that have to happen during this nucleation. And what we've seen was that, initially, in solution, you have actually species that are like PBI4, so more tetrahedral type of species, no octahedron. But if you do the metadynamics along the collective variables, at some point you find actually intermediates where now octahedrons are forming. And at some point you actually find that these octahedron are kind of clustering together into edge-sharing aggregates that look very much like PBI2 and these are surrounded by the monovalent cation. So you have here the lead iodide clusters, and around you have this monovalent cation. And then, what is a really important step is that now the monovalent cations have to diffuse into this and break this edge-sharing octahedra to make actually a corner-sharing network that then allows to have a critical kind of seed that can grow into a full type of perovskite structure. So this step, that is actually the monovalent cation that has an important function, that was really an important finding. And indeed, collective variables that we were using at the end were coordination numbers, and especially also including all the coordination of interspecies coordination between the monovalent cations. We did also something similar for the 2-step process, also using actually 2 different approaches, 2 different enhanced sampling techniques, and also there we could find that indeed, if you have the lead iodide, it's the kind of diffusion of the monovalent cation that forms an intercalated structure that then gradually can actually form, again, perovskite type arrangement. And we could also show that in principle, even though this material indeed can exist in these 2 polymorphs, perovskite structure and something else, there should be kind of a direct pathway to form directly the alpha phase. Usually alpha phase is formed after annealing, heating up to high temperature, and then maybe kinetically trapping this phase. And that this indeed is the case, we could also see from some experimental findings. So there are some in situ X-ray, synchrotron X-ray scattering experiments that actually show that indeed, if you follow this, you have first the PBI2 disappearing, but you have an appearance actually of perovskite phase that then slowly gives in to the thermodynamic, more stable delta phase. And we could also kind of describe the relative energetics of these different intermediate states for different systems, with iodide, with bromide, with different monovalent cations. And indeed, for this 2-step process is the dissolution of the ions for the intercalation process. So again, the monovalent cation that play a very important role and kind of constitute the rate determining step. So from this, okay, we've certainly gained some qualitative understanding, and it was also interesting that both procedures actually involved a very kind of important role of the monovalent cations. The monovalent cations are always considered as kind of not very active bystanders because they don't contribute directly to the band edges, so electronically they don't really have a direct impact on the band gap, but certainly structurally and from a nucleation point of view, they play an important role. And in this kind of conversion from this PBI2 structure, it's actually important to stabilize the kind of corner sharing state, and this you can also do if you use other anions, and experimentally, actually, indeed, they could show that they have a better conversion by using chloride, which we also predicted. Okay, so what about compositional and interfacial engineering and the effects of additives? And I will show you in a minute what I mean by additive, but you can certainly imagine that always the most vulnerable point of the material are surfaces. So surfaces exposed at grain boundaries, surfaces exposed at interfaces. This is always where, okay, you have the highest tendency to maybe form defects, or where you have problems in kind of transporting charge carriers efficiently. And this is often what is targeted by putting additional things into the preparation, but often also as a posteriori treatment of the different layers. Okay. Okay, so additives can be many, many things, and people have been trying many things. You can have very small ionic, anionic, cationic species. You can have bigger organic cations. You can have neutral things. And okay, they can interact in so many different ways. So even to start from a computational point of view of, okay, where is really their kind of site of action, sometimes not easy. Indeed, as I mentioned, they can bind to surfaces, to grain boundaries, to interfacial different interfaces, and they can also form sometimes quasi two-dimensional structures, and there are many different ways that they can have beneficial effects for the material. They can passivate defects, they can shield the surface, they can stabilize the surface, they can enhance charge transport. So really difficult problem from a kind of simulation point of view. And during the years, we have been looking at many, many different additives and all of these different scenarios, so I'm not going to show you all this, but I try to kind of summarize a bit some of the take-home messages that we found. So first one is, okay, if it's small, then maybe we have incorporation directly into the lattice. So indeed, you can find that, and you can actually even use this type of incorporation by mixing cations, and actually is one way of getting rid of this competing thermodynamically most stable delta phase, because actually through the mixing of different monovalent cations, for example, here you have cesium lead iodide and formaldinium lead iodide, their most stable, thermodynamically most stable forms are indeed delta phases, two different delta phases, and you can, by mixing, you can actually get rid of the delta phase, because the two delta phases are structurally so dissimilar, whereas the perovskite phases are much more similar together. And I see that Laura is getting a bit nervous, so I will go a bit faster. So indeed, you can have passivation effects, you can have shielding effects of the surface, so it's very important that you form actually very commensurate superstructures that are shielding the surface from ingress of water. and that indeed leads to high stability devices. And also, in the case of lead-free devices, maybe the closest possibilities are tin devices that are super sensitive to oxidation. So with some of the additives and commensurate superstructures, you can actually stabilize the oxidation state of tin, and we have a kind of record tin-based perovskite phase device due to that. And I think I will stop here by, also thanking all our experimental collaborators. We're working in very close contact with the group of Michael Grätzl, but also with many others of the experimentalists. And of course, I would like to really thank Michele for all his contributions, and also for really teaching us so much, and for his support, and for him as a great mentor too. So, tanti auguri, Michele.
When you do this predictive work, is there the risk that sometimes, even if you put in the right components and so on, you end up with a material that doesn't have the phase of a perovskite? There is so I don't know, the topology is different, so sometimes there is, so they try to make a material and it's not a perovskite. Is it something that you have encountered?
Yes, especially also with the, I showed you already, they are polymorphs in any case, so they can be competing structures, but they usually know this to control this experimentally. With the additives, indeed, you can have these layered structures, quasi two-dimensional or quasi one-dimensional, and indeed some of them are competitive, and we could predict some of the 1D phases that were competitive, and that explained why they actually didn't see what they were thinking. And the usual way that at least we can validate that we kind of have the right structure, that's not always so easy, is because we don't have usually fully resolved crystal structures, but we usually have at least powder diffraction spectra, so we can simulate powder diffraction spectra from our structures and then compare. And sometimes we have also other indications from infrared or Raman modes for the additive binding.
Another question. Come on, don't be shy. Yes? Okay, well, if not, let us thank Ursula again, and maybe you can catch up with her afterwards. All right, the next speaker is Davide Donadio from UC Davis. No, I was just looking there. I said, no, it's not. Well, maybe also you have collaborators there.
Yeah, I was putting on the collaborators. Otherwise, I always run late, and then I forget to I don't have time to acknowledge them, and it's important. All right. It's a great pleasure for me to be here at this conference that is going to be a landmark in the history of molecular simulations, and at Michele's birthday, especially at Michele's birthday. And there is a little problem with that. So Michele's birthday is the 7th of November. My wedding anniversary is on the 8th of September, and my wedding anniversary is on the 8th of September, that is today. And I'm always at Michele's birthday. My wife doesn't like it. All right. So today I'm going to talk about ice surfaces. Everybody, or most of you know that I love ice in many ways.
especially to walk on it or climb on it. And being in Lugano, I was there in 2003 to 2006 in Michele's group, and we took this picture in 2005 for, wanted to make like a birthday card for your 60th birthday at the time, I think. So Michele is not in the picture because it had to be a surprise, but it was really a wonderful group, and the experience in Lugano is what really led me to what I am now in terms of scientific career, and at the same time we were having an incredible lot of fun. And at the time I was working on nucleation using metadynamics. That was the big new thing at the time, and I think we did the first simulations of crystal nucleation in a Lennard-Jones system, and time like stopped because this year I was publishing a new nucleation paper. In this case, just a little more complicated system. It was liquid carbon that goes into graphite and diamond. And I was tempted to talk about this, but then Ali was like, no, I want to hear about ice, so I'm talking about ice. Why am I interested in ice besides my mountaineering activity? Is because it's an incredibly important catalyst of reactions that have an impact on the chemistry of the atmosphere, both at low altitude in the, so these are reactions that happen in the snow and then control the chemistry of the atmosphere down to Earth, and also, so there is like photodissociation of organic molecules or nitrate photochemistry, but also in the stratosphere where this type of reaction seems to be catalyzed by polar stratospheric clouds, so at much lower temperature than down here, and it generates molecular chlorine that eventually leads to ozone depletion. So it's an important environmental problem pretty much all across the board. And it's a difficult problem. So the question that we were trying to answer in this set of projects that have been funded by National Science Foundation in the past like 6 years, I think. So there's a big amount of work in collaboration with experimentalists. The projects were triggered by the observation that organic molecules and also nitrates photodissociate much faster when they are absorbed on ice surfaces than when they are solvated in water. And the question was why? So why are the reactions so much faster? So why is ice surface such a good catalyst? And specifically at molecular level, trying to understand what is the effect of the solvation environment. So modeling this system as common as ice can be is complicated. Well, it's obviously complicated because these are photochemical reactions and you know how hard it is to simulate them. But before that, you need a molecular model that is able to describe well the thermodynamics of ice and water on different scales. And since you're interested in catalysis on a surface, you need to have a good representation of the surface. So this is a dynamic surface in the same kind as the surfaces of the heterogeneous catalysts that were shown in some previous talks. Besides that, you want to simulate chemistry and photochemistry, so you want to understand the electronic structure of these surfaces quite well. So you need good models that take into account the proper electronic structure of the surface, especially if you think about simulating photodissociation of nitrate. The homolumo or gap of nitrate is around 4 electron volt, and that is well within the energy gap of water or ice. The problem is when you simulate water or ice with density functional theory, the actually homolumo gap becomes around 4 electron volt, and then all the chemistry you see in your simulation is biased by that. So you need to take that into account. And then there are hydrogens around, so you have to consider nuclear quantum effects. And then you have, if you want to simulate photochemistry, you need to be able to calculate UV visible absorption spectra of the absorbates at solvation conditions. And eventually, when you learn all these things, you can go on and try to sample the reaction in the excited state, which is extremely difficult too. So since the last two items, there is not time to cover this couple of items here, I will stick to the description of our catalyst without putting any molecule on. So the first couple of slides are going to describe the first two items there. So we are interested in a model that reproduces well the thermodynamics of ice and water and on different scales, and I'll talk about some machine learning potential that can do that quite efficiently. And then they also allow efficiently to simulate nuclear quantum effects by path integrals, so that enables some other type of simulations. So the type of model, the question that we're asking ourselves is, what is the effect of nuclear delocalization in bulk ice and water, not just on the structure, which is well known, but on the electronic structure at relevant conditions and in a coherent set of simulations. So to do that, to enable a fast sampling, we're using standard machine learning potential of the, let's say, feed-forward neural network type, so like the better Parrinello type, but kind of boosted. So we're using deep MD potentials from Roberto's group, and this class of potential that are called new revolution potential that have been developed by a collaborator in China and in Finland, so it's a bit delocalized. So we are using these to sample bulk ice, bulk water, and then eventually ice surfaces, both with classical dynamics and path integral molecular dynamics, and we have here a former master of path integral molecular dynamics, or effective path integral molecular dynamics, that is sitting there behind Michele, the other Michele. And then we are interested in accurate calculations of the band gap of this system, and for this we use many-body perturbation theory. Going to the water model that we are using, we fitted this new revolution potential. So I'm not going to talk about the deep MD that we use because that is pretty standard. It has been fitted on SCAN, and in this paper, it's not been done by us. It was already there from collaborators, from Marcos and Roberto's group. So I want to spend a couple of words about this work we did on the new revolution potential. We trained the new revolution potential on the RevPB0D3 data set published by Christoph Schran. It's a relatively small data set of about 1,000 configurations all across the board, but they are carefully chosen to cover different ensembles, different environments, local environments, and the new revolution potential that we fitted is quite effective at simulating the water anomalies. As you can see, it captures the density minimum down here in supercooled water and the density maximum with a pretty close representation of the temperature of maximum density. It also reproduces well the difference in density between water, that is represented here, and ice. We were interested also in having a look at other anomalies. We look at the heat capacity. We have this maximum in heat capacity that has been seen experimentally in supercooled water, and we kind of reproduced that. As you can see here, we are off by quite a bit, quite a few R with respect to experiments, but this is because these are classical simulations, and water is inherently quantum, and quantum effects on heat capacity are huge. So we are now running quantum simulations, and we are getting pretty much in line with the experiments here. What this new revolution potential enables, so its implementation on GPU cards enables very large simulations on basically desktop workstations. These are simulations that I ran on a workstation that I have on my desk. It keeps my office warm. It has just 4 gamer GPU cards. And I can run systems like this. This is a two-phase simulation that we use to calculate the melting point. Half the box is ice, half the box is water. And this is around 10,000 water molecules, so 30,000 atoms. And this is our estimate of the, let me use this, of the melting point. It's, okay, it's overestimated by a little bit compared to the real thing, but not too bad. Talking about performance, basically you can achieve with this new revolution potential, you can run on a desktop workstation several nanoseconds per day. This is 3 nanoseconds per day on 4 graphic cards with around 30,000 molecules. So it's very effective. It's pretty much getting in the ballpark of performance of classical potentials like TIP4P. And this is a whole summary of thermodynamic properties that we calculated. I don't want to go over too many details here, but we have a good representation of most of the thermodynamic properties of ice and water, except perhaps the surface tension, which is off by 25%, and the compressibility, which is quite off as well, and I think it's mostly the fault of the training method, basically, the running on RefPB0D3. So now that we have validated, let's say, the structure and the thermodynamics of our water model, we can address the problem of what are nuclear quantum effects, what is the effect of nuclear delocalization on the band gap of fundamental band gap of ice and water. And this is what we started from. We had pretty accurate estimates from works mostly from Alfredo Pasquarello on water. Here they estimated from a combination of molecular dynamics and path integral simulations using self-consistent GW, that the renormalization of the gap is about 0.7 eV. And comparable, to compare with ice, where lattice dynamic simulation led to an estimate of a 1.5 eV band gap renormalization. So another question that arises here is, why are these values so different? So we wanted to simulate everything on an equal footing, which means we did molecular dynamics and path integral for both water and ice at the same temperatures, or at similar, well, water at 300 Kelvin and ice at 260 Kelvin. And we found results that are pretty much in line with what was in the literature. So the renormalization of the band gap in ice is a reduction of 1.2 eV, and in water is around 0.8 eV. So still a large difference. Another thing we noticed is that the two neural net potentials, the DNNP fitted on SCAN and the NEP fitted on RefPB0D3, were giving pretty much the consistent results. What we found is that the main effect is a raise of the nuclear quantum effect raise the valence band and have a minimal effect on the conduction band. So we wanted to investigate the molecular origin, so we went to look at this, at the structural fingerprint of quantum effect, which is the proton transfer coordinate. Basically, if you have a hydrogen bond, you have one is a covariant, you have a covariant bond for the hydrogen involved in the hydrogen bond on one side and a longer hydrogen bond on the other side. But due to the fluctuation of the bond and enhanced delocalization, you may have a situation where the proton goes a little bit on the other side. So the difference between these two lengths is called proton transfer coordinate, and it can be sampled in classical dynamics, as you see here. These are comparisons of the two different machine learning potentials, and in path integral dynamics. And you see that when you switch on path integral, both in the case of water and in the case of ice, you have a delocalization of the proton and some and a non-zero probability of having the proton on the other side of the dividing line. What really strikes here is the difference between the quantum effects in water, so the broadening of the distribution of these distributions in the case of water and in the case of ice. And the broadening in the case of ice is much larger. So we plotted the width of the distribution against the fundamental gap for a bunch of configurations. And you see that when you switch on quantum effects in water, the broadening of the distribution remains similar, but it kind of correlates to the fundamental gap. When you do it for ice, you have a much larger broadening down here, resulting in a much larger reduction of the fundamental gap. So that means that the delocalization of the proton is the driver for the renormalization of the band gap. Now, if we want to go to surfaces, then we need to go back, and we have experiments that have probed the surface. This dates back to my times at the Max Planck, when I was collaborating with Misha Bond's group, who does some frequency generation experiments on the surface of ice. And what they see is, looking at the some frequency generation, so the vibrational band, OH band of the ice surface, they see this trend where the first moment, so the blue shift of the OH stretching band, as you raise the temperature, so as you go down here, decreases in intensity and shifts to the blue side, to the blue, yeah. And this shift is not linear with the temperature, but it has this kind of stepwise behavior, which changes depending on what kind of surface you're looking at. And we try to interpret this stepwise behavior in terms of melting through classical simulations done with traditional models like the T4P ice model. So we're looking at several indicators. The simplest one to look at is the density profile. So here we have a large-scale model of ice, surface of an ice slab, and you can recognize the ice bilayers here and the disordering of the top and the bottom layers. So taking the density profile of these bilayers shows these peaks. Here is the fingerprint of the bilayer. When the peaks disappear, it means that the bilayer is getting more disordered. And then you have very deep wells, deep valleys between the various bilayers. So looking at those, you can characterize the melting behavior. And what we found is that basically you have a sort of stepwise melting. So when as you raise the temperature, at low temperature only the top layer is disordered, and then all of a sudden when you switch on the temperature higher, you have a sharp raise of the valley between the first and the second bilayer, and a disordering of the second bilayer. And this kind of corresponds to the stepwise function that you see in the experiments. And on some surfaces, like the basal plane surface, this is much more marked than in the first prismatic plane surface. Now, with machine learning potentials, we try to reproduce those old results, and we see pretty much the same effect in classical MD simulations. So these are new results on the same story. When we switched on quantum effects with path integral molecular dynamics here with the new revolution potential, we see pretty much the same behavior as in the pre-melting behavior is pretty much the same as the classical. So we can confidently say that quantum effects don't really have any major impact on the pre-melting behavior of the surface of ice. However, they still have an impact on the band gap renormalization, also when you look at the band gap of the surface. So we did the same as before. We calculated the band gap of the slab and compare it to the band gap of the bulk. In classical simulation, so the solid color histogram is the band gap of the slab. The shaded one, the shaded box here is the band gap of the bulk. Blue is classical and green is path integral. As you can see, we have, again, a substantial renormalization of the band gap in the case of the slab, but the renormalization of the band gap fades as you increase the temperature. So we have more of an ice-like renormalization of the band gap at low temperature, and let's say more of a water-like renormalization of the band gap at higher temperature. And you can see here as well that this is a electronic density of state, that the renormalization of the gap is mostly driven by a shift in the valence band, in the top of the valence band. Right, so to get some interpretation of that, we can look at the isosurfaces of or the Consham orbitals of the valence states. So we have the HOMO. Oh, I thought I've written. Okay, we have. This is the HOMO of the ice slabs. You see that these are and the HOMO -1 and HOMO -2. These are localized states, and these are the LUMO states, which are much more delocalized. So the delocalization of the proton is much more impactful on the localized states of the localized valence states. Now I wanted to characterize try to solve another problem, which is characterizing the ice surfaces at very low temperature. So going in the direction of understanding surfaces for polar stratospheric clouds that is below around 150 Kelvin. And the question that we were asking that was still somewhat unresolved in the literature is whether surface vibrational spectroscopy can tell us whether the surface is proton order or proton disorder. And so just a brief explanation of some frequency generation spectroscopy. I mentioned it before, is an experimental technique, nonlinear spectroscopy technique that consists of shining a visible light together with infrared light and collecting the infrared absorption here. And the intensity of the SFG signal in the infrared frequency region corresponds to the vibrational signal and can be calculated through linear response theory as the Fourier transform of the correlation of the dipoles with the polarizability of the system. And this contribution is surface sensitive because this cross correlation goes to zero in a homogeneous environment. Now, there are experiments. These are very difficult experiments, especially when you go and collect the imaginary part of the SFG signal, which is collected in heterodyne some frequency generation spectroscopy. Here we are collecting two different experiments that look extremely different, the green and the red, and some simulations that are somewhat in agreement with one experiment, not the other. And here are several different simulations that give rather different results. So one of the problems is, of course, the level of the simulations. The other problem is that often these simulations are not well converged because these correlation functions converge on very long time. So we use a deep MD model where also the molecular polarizability and molecular dipoles are fitted through a deep neural network. And this was already tested by Marcos and Roberto's group in this paper. We tested on we tested the Raman and infrared spectra of ice and water, which give pretty satisfactory results compared to experiments. And then we look at two different slabs. One is an ICE11, which is proton order, and the other is a typical ICE1H cut, which is proton disordered. And you see that the infrared, this is the infrared absorption of the whole slab. The two infrared signals are very different. These are resolved by layer by layer. So you see that the difference stems from the first two bilayers. So this is especially the first bilayer is the purple line here. It has this double peak in ICE11. It also features a double peak in ICE1H, but in proton disorder ice, but it's a much smoother one. So the first question we were asking ourselves is what layers contribute most to the SFG. Of course, we have the top layer that gives the most of the signal. These are the homodyne and the heterodyne signals. In both cases, the top bilayer is the main contributor, and then we have a minor contribution from the second layer. And then we can now compare our results to experiments. In the case of the heterodyne, I think our simulations are not conclusive because the differences between proton order, that is the red, and proton disorder, that is the red, and proton order ice surfaces is rather minimal here. It's just this shoulder here. But if you look at the homodyne spectrum, and this is the experimental one, the difference in intensities between the weakly hydrogen bonded band and the free OH band here is in much better agreement with experiment when you simulate proton ordered ice. So we did some work on the interpretation. You can basically interpret this spectra in terms of single OH stretching movements by taking the power spectrum of the OH bond and reweighting it with their orientation. I don't think I have time to go into the details here. What I can show is also that calculating the heterodyne and both the heterodyne and the homodyne spectra of different facets allows us to, in principle, differentiate from one facet to another. So we can tear apart the basal plane, the primary prismatic plane, and the secondary prismatic plane. And here we have the conclusions that I don't think I want to go and read. But I want to give you an outlook of what we are doing next. So we are going to go into much more complex ice surfaces like this one.
Thank you very much. Very exciting. Questions? Michele Ceriotti.
First layer melts. This is done at constant number of water molecules, right?
Yeah, it's a slab.
And have you ever thought of doing this at constant chemical potential? Because I could expect that maybe the surface becomes more stable with one more or one less water molecule. I guess you could see this as a finite size effect, but I thought this could be interesting to check.
Yeah, exactly. We tried like a full layer and a half layer. And of course, the half layer melts faster because you have a lot of broken hydrogen bonds. We didn't test constant chemical potential in any ways, but we went very large. So we have works with classical potentials where we go to, I think it's all the way to 10,000 roughly water molecules in the slab. So you have a very large patch. And you don't see a major difference in behavior. So certainly you don't get water desorption because that is too rare an event. But yeah, we didn't see any specific defects that form, especially when you make it proton order, it stays perfectly ordered.
So okay, very quick question and very quick answer. Go ahead.
Ions in ice.
We have a work where we absorbed sodium chloride at different concentration at the surface of ice. We see, first of all, we see a zeroing of the differences between the various between the two bilayer surfaces, and an increased thickness of the pre-melting layer.
Well, let us thank Davide again so much.